recognize crosswalks and traffic signals has struck me again. And again, I have no idea why I'm so challenged by the concept of a crosswalk and a traffic signal, but apparently I never really learned those at some point in life. Am I the only one, by the way, that totally sucks at doing that, at distinguishing a traffic light? Traffic signals are, they're suggestive, they're not demanding. Yeah. Yeah, so shoot, I needed one more person. So yeah, so Tiffany was kind enough to send me an update on like what you guys had voted on. And there's one thing that says nucleophilic substitution and terpenes. That's going to be actually a ton of mechanisms. I mean, SN1, SN2 are mechanisms. The carbonyl lecture, we're going to cover mechanisms. And then the terpenes, we're going to look at a little bit of diene mechanisms. But like, for instance, we won't look at alkene mechanisms or alkyne mechanisms or benzene mechanisms because they're not tested on the MCAT. But between the carbonyls lecture, the nucleophilic substitution, half of that is going to be mechanisms. And so, yeah, those will be filled in. So I'm going to add gases to one of the open spots. And then I'm going to leave that other spot probably open for another week or so to see what the gut feeling is. Because I think what you'll want may change as time progresses. And then just heads up on what next Tuesday is going to be. Next Tuesday, I'm going to go over AAMC practice items from chem physics. So I'm going to pick about 6 to 8 freestanding questions and then 2 of the passages. So passage 1 for sure. And I think the second one I chose is passage 7. It's whatever one has the line mover Burke plot on it. And just want to try to do all the chem within context. But the big thing, it doesn't matter if you do them ahead of time, don't do them ahead of time, it makes no difference. The whole reason I'm doing them is more to get just familiar with their style of questions. So it's all about what did the passage give me? What do I learn from their questions? And basically, it's the art of reverse engineering AAMC's writing to determine like what to expect on test day. And so it doesn't matter if you haven't done them, don't worry about it. It's not going to ruin any full-length exams. Going to ruin the practice items for you. Okay, so want to go ahead and get started on this. This is kind of a heavy load for this one, just because normally thermo is its own lecture in of itself. Oh shoot, I just realized I need to exit out and make somebody co-host because it figures as soon as I did the screen on this one, somebody came in. So let me, Alexandra, do you mind? You're this top alphabetically. Do you mind if I make you the co-host? Okay, thank you. A lot of pressure. So if somebody gets in and you don't let them in right away, we're all going to yell at you. So hopefully you can deal with that emotionally. Okay. So thermo and kinetics on the MCAT, the reality is you're going to apply thermo. Yeah, lots of abuse coming, by all means. But you're going to apply thermokinetics probably more to biochem than you are to GChem. But this is the GChem foundation. And with every single thing we do, I want you to stretch it a little bit further and ask yourself, what happens when we do this for biochem? Because again, when you took biochem, how many had a professor that asked about the delta G for an overall process, or identify what step was like a committed step, what step was a point of regulation based on either the enzyme you used or the delta G? Yep, they love those, okay? And then how many in kinetics had to learn a couple graphs for biochem? How many definitely, oh, sorry, wrong color. How many definitely saw this one? We have V, substrate concentration, and then 1/2 V max. And that's your Km. Let me write that more neatly. How many have seen that one plenty of times? That one is very familiar. We're going to look at that first from a GChem perspective and then turn it into something we know from biochem. And then how many have definitely seen the Lineweaver-Burke plot? And know that this is like 1/S, 1/V, and that this tells me about 1/Km, negative 1/Km, this tells me about V max. So am I safe in assuming that these two graphs, for those of you who've taken biochem, are familiar? Perfect. Okay. Familiar looking, yeah, it doesn't mean you know them, but you've seen them. I would say for these, brushing up is an understatement. Got to know how those work. Okay, so we're going to finish off with kinetics, and ultimately I'm going to do GChem, but then tie it into how it becomes those. In the end, probably a 80% chance everything I'm doing today is going to be applied to a biochem example rather than a GChem or OChem example. But it's kinetics is still kinetics, thermo is still thermo. Okay. So starting into it, thermochemistry is basically, oh, we did not get the handout because I spaced out. Not my day. Not my most glowing performance. Okay. Yeah, I'll blame the traffic signals again. It's just seriously, I must panic at that one. I always get that wrong. Okay, so Gen Chem handout. Sorry, it says 9. That basically doesn't mean much other than it's number 9 in my grouping. So it should pop up now. And I think all the handouts for anything I do, I think Discord has them all as well. I think Tiffany and Jonathan have been awesome about loading those up. So if you want to see them ahead of time, I usually try to send them a little bit earlier. Yeah, thank you so much. So yeah, so you can get them ahead of time. I mean, I should always load them up. That was my fault for not tossing them in there. But if you want to see what's going to happen ahead of time, always a good spot to go. Okay, so thermochemistry as opposed to thermodynamics. I want to emphasize the difference. Thermochemistry is the heat, the energy associated with a chemical reaction. Thermodynamics, dynamic meaning motion, is how we apply that heat, how we use it. So for instance, does a car run on a combustion engine? Is that pretty much what our, well, okay, they're electric engines now, but electric motors, but we have a chemical reaction that generates heat, but then do we have to harness that heat by expanding a piston? That piston moves a rod, which turns a wheel, which turns a crank, which turns our tires. So there's a process of harnessing it called thermodynamics, how we take that thermal energy, that heat energy, and turn it into work, turn it into heat that's been relocated somewhere else, turn it into light, turn it into some other form of energy. But thermochemistry generating it, thermodynamics moving it. So we want to break it into thermochem followed by thermodynamics. I'm assuming these are familiar from GChem, OChem, and biochem, but are there cases where you start with a certain energy level for all your reactants, it goes up to some excited state, some intermediate, some transition state, depending on what it is. This case would be transition state because it's just there for a brief moment. And it comes and finishes in the end. So a couple things. Number one, energy. Could energy be heat energy? Could energy be free energy? So could it be enthalpy, delta G, or G, I should say. It can be anything. I'm not going to specify right now, but it can be any type of energy. Why is this axis not time? So I'm going to change it to time. Will you tell me if that's right? Can I just put time there? Because when we go from a reactant, doesn't it take time to go from the reactant to a transition state or intermediate, depending on the mechanism, and on to a product? I mean, is it true that over the course of time, it converts from a reactant to an intermediate to a product, or a reactant to transition state to product? So why don't they say time? No, there is actually, we could monitor energy over time? But exactly what Brooke just said. Can time go backwards? Is there an unsend button for those emails you regret? Nope. But can reactions go backwards? Oh, is there an unsend button now? Oh, or are you saying yes to reactions go backwards? Oh, I need that. You know, I think I did read about something like that for drunk texting or something. At certain times of night, you can set your thing to not send right away. But reaction coordinate, from the start of reaction to middle to the end, chronologically in the forward direction, but because reactions go backwards. I wish I could. Now, I don't send texts I regret. I send typos I regret. And I have definitely I'd sent a few awkward texts in my life because of spell correct. So I'm sure we all have. Okay, so for this one, what is the difference between these two reactions? Can you just looking at them, tell me what is different? In the first case, you agree energy is being released. It's going from high energy to low energy, so energy is released. Second one, lower to higher, you have to absorb energy. So I need to be a little more focused. If this was enthalpy, then that means heat going in is less than heat coming out, so there'd be a net release of heat. It'd be exothermic. Oh, dead professor. That would be a hard one to work around. That's yeah, because D and R are so close to one another. Well, hopefully that all worked out. Death threats always, yeah, not a good one. Dear soon to be dead professor, if you don't give me my grade. Oh, sorry about that. And are you banned? Do you have a restraining order from going anywhere near that office? Okay, but energy released, energy is absorbed. If it's heat energy, then it's exothermic. If it's heat energy here, it's endothermic. If it's delta G that we're looking at, so free energy and delta G, we'd say this is favorable or exergonic. Perfect. And then this one would be unfavorable or endergonic. So activation energy, I want to mention, why am I calling this the kinetic zone? It's a transition state. It's the least stable point in the process. But why do we call this whole region here kinetic? From start to that highest point? Exactly. This dictates how fast it can go. So if I drew this reaction like this, is that a more favorable, less favorable, faster, or slower reaction that I drew in yellow? It is not more favorable or less favorable because you start and finish at the exact same point, so favorability is the same. It is faster. Why is it faster? It takes less energy to get to the transition state, so more molecules have enough energy to overcome that barrier, and it'll go with that. So for instance, if I told you this was catalyzed and this was uncatalyzed, would you believe me? No, because I lie all the time. Okay, no problem. Then what if I told you this was the intermediate, but this was an enzyme substrate formation, PGO? Would that be a little more reasonable? Ah, perfect, because enzyme, do you agree, enzyme substrate is a type of intermediate, but is it a more stable one because it helps the kinetics? Is that true that enzymes lower the activation energy? So this would be the intermediate if it had no enzyme helping it. This intermediate if the enzyme is helping it. Oh my gosh, it's old lingo. since the day I first started teaching this, so TGL, Todd's gonna lie. 75% of the time, I'm going to lie to you because 75% of the time, the answer or explanations are wrong. Only 1 out of 4 is correct. So it's the same thing. Do not trust the thing I say. Cognitive lying disorder. I like it. Yeah, favorability has nothing to do with how fast. Favorability has to do with starting and finishing energetics. How fast has to do with the kinetic, the excitation, the activation energy. So activation energy is from highest point to the starting point, reactant up to transition state, whereas overall start to finish is your energy released. Okay, let me add a few more things to these graphs. If it's delta G, we call it exergonic. Energy is exiting the system. If it's heat, it's exothermic. So everything in chemistry, is it based on the system or the surroundings? As a chemist, do I care about chemicals or the world? I care about the chemicals. I care about the system. Everything is system-centric, meaning if you touch a reaction that's exothermic, yeah, the chem book may say it's negative delta H, and that may explain that heat is going from the system, the chemicals, to the world around it. But if you touch it, are you the world or are you the chemicals? You are the world, meaning if you touch an exothermic reaction, although it's giving away heat, are you giving away or gaining heat? You're gaining heat. It'll feel hot. Okay, somebody asked a question, do enzymes affect the entropy? And it's a loaded question because overall, no, because the enzyme is regenerated in the end. But does it lower the entropy perhaps of the transition state? So does it bind it in a very specific way that that substrate can only align one way and is not free to have like different rotations, different orientation? So the transition state or enzyme substrate complex has limited entropy for the substrate or the enzyme, but overall, because the enzyme is regenerated in the end, then we're going to say that no change by the end. But how many learned, certainly in biochem, they made a huge ordeal about enzymes and like how proteins fold or how they renature, denature, affecting entropy. So really good point. I'll probably hold on to till we have the entropy page to get into it. But how many learned that protein folding from a protein standpoint is terrible for the entropy of the protein? It goes from random to very ordered. But how many learned that water is bound to the protein, and when the protein folds into its natural state, its well, I guess non-denatured state, did you learn that it releases water? So what it lost in its personal freedom, water made up for it by gaining freedom. The waters that were bound to the protein when it was linear and random are now free to swim anywhere they want. They're not bound to the surface of the water. Bulk phase water, exactly. How many learned something about that? That you trade one for the other. The protein may lose randomness, but in exchange, water gains randomness. So in chemistry, we call it the solvent cage theory, that around every molecule, there's a layer of solvent, whether it's water or whatever it may be, and that whatever you gain in organization of the molecule, you have a counterbalance of the disorganization of the solvent cage. But if the solvent cage organizes around that atom, then you lose entropy based on the solvent having to organize and form a layer around it. So it's basic theory. You worry about the molecule and what's around it. Yeah, and you think about it, energy can be transferred. If you, let's just go with that. So it can be easily lost or gained depending on what your perspective is. The system can lose it to the surroundings, surroundings can lose it to the system relatively easily. Entropy energy, heat energy, free energy. For Elton's comment, I'm going to put a little caveat on that. Yes, according to thermodynamics, is the world falling apart? Perfect. So the entropy of the universe is tending to disorder. It's increasing. But we still, for whatever reason, tend to think if something gains entropy in one spot, something lost it somewhere else. So we tend to, in chemistry, think in the instantaneous moment that net entropy is zero. When something becomes random, something else becomes ordered. But the tendency of the universe, supposedly, because is the universe contracting or expanding, at least according to our science theories? Expanding. Consequently, if something is expanding, it's getting more random or more ordered. More random. So more chaos. It's spreading out. So consequently, we see the universe as tending towards an increase in entropy because it is an expanding universe. But for chemistry, although that's completely true and it's a law of thermodynamics, we still have a tendency to say if delta S is positive for the universe, or for the surroundings, excuse me, then it's negative for the system and vice versa. We assume sign inversion, that when one gets more ordered, the other one gets less ordered. And how many have definitely ran into that? Like what happens to the system and the surroundings? And the beautiful thing is the MCAT, because they know there's a sign convention issue between physics and chemistry when it comes to system versus surroundings, they usually word it in a way where you have to decide system or surroundings. So I guess let me go ahead and finish the words, and we'll get to entropy in a slide or two here. But exergonic, energy is released. Exothermic, heat energy is released. As opposed to endergonic, heat is entering the system, or entering heat energy or free energy into the system. We define these as positive delta G and delta H because energy is going into the system overall. As opposed to here, energy is exiting. How many have seen these graphs enough that this is not news? I'm basically just regurgitating what you probably already know. And am I safe in assuming that these are old news? Might be a strong word, but yeah, pretty much you've seen these ones. Okay, so for me, if I'm writing a passage, do I have to assume you know this and screw with you? Yep, I got to screw with you. Somebody just asked a question, which is a perfect way to screw with you. Is there a difference between delta G and delta H? Oh, I guess I don't have to screw with you, but it is my job satisfaction. Okay, so what is the fundamental difference between delta G and delta H? Why do we have two different things? Why do we not treat them synonymously? So free energy, energy available for molecules to carry out whatever it needs to do. So energy that's free and available for chemical processes. That comes in two flavors. It comes in heat energy and it comes in randomness. So delta G takes into account entropy and delta H, whereas delta H is only heat. That's a fundamental difference at the MCAT level I'm going to worry about. So one of the examples we talk about is the randomization of any fiber. Yeah. Yes, and somebody brought up the ever so annoying zero that can also show up on these. So I'm going to ignore that for a second and just do the general one, and then we'll get specifically into what that not means. Okay, so delta G, delta H, and T delta S. So a really good example, I'm going to get ahead of myself. It's coming up in a couple slides, but it is kind of cool. But if you take a rubber band and it goes from stretched to relaxed, is that natural or unnatural? If you stretch your rubber band and let it go, does it want to stay stretched or does it usually recoil? It recoils. So can we conclude then that delta G for that process would be a negative number? And why do I say it's negative? Favorable. By our definition, a negative delta G is favorable. Okay. It ends up, it's kind of a weird thing, but if you, I kid you not, this is a real experiment, but if you stretch it, rest it gently on your lower lip for just a split second so that you're convinced at a certain temperature, move it away from your lip maybe a half inch or so, let it relax, like let it contract really fast, and then put it against your lip right away, it will feel cold. Totally bizarre, but it actually will feel cold. So, okay, so question. Favorable, it also has potential energy in a way, right? Which is another way to see the energy. I'm going to ignore potential energy and call that a chemistry. No, I'm going to call that more of a physics term. But there is, I'm going to tell you this right now, this has a lot to do with potential energy in the sense, organizational potential energy, for lack of a better term. If I spend a lot of time organizing something, can it fall apart and give me that energy back? Can I stack my papers just right? When they fall apart, I get that. So I'm going to shy away from calling it traditional gravitational potential or spring potential and just refer to it as chemical bond energies and organizational energy. Oh, how did that work out for you? And again, this made me so pleased when you said you did that. I got incredible joy, and I told my wife, really, you have line up, well, okay, you need to fill it really close to the top. Like basically you need to put fill the glass close to the top, put a straw in it, and have less than a half an inch. But if you do that, put the other straw across it and blow really, really hard, you will suck the water up and spray it at somebody. And the way it really helps, make the other person look down the straw you're about to blow into to make sure it's lined up the right way. And then because it's something mean and evil, it'll work better. Because when you blow it out, you will definitely spray them with a bunch of mist. Keep in mind, they won't be your friend anymore, but that'll give you more study time because friendship notoriously takes away from precious study time. But for this one, it feels cold. So tell me what feels cold means. Delta H is negative or positive? Endothermic? So perfect, positive number. So we have a negative number for delta G. We have a positive number. So what does this have to be? This has to absolutely positively be a positive number that is significant or small. Has to be positive and significant, exactly. Okay, somebody asked for something to be re-explained. I got to get my cursor up and functional to roll back. Oh, okay. So the question is, why would something where heat's being absorbed be cold? Again, are you the surroundings or the system? Are you able to touch the chemicals, or do you touch the outside of the flask that holds the chemicals? So you're part of the inside or outside of the flask? Hopefully, if you're inside the flask, call 911. We are outside. So if you touch something that feels cold, does that mean it's giving you heat or taking heat from you if it feels cold? It's sucking your heat away. So if you touch something cold, you'll freeze to death or catch fire. A little bit extreme. Yeah, exactly. When you touch it and it feels cold, it is sucking heat from you. So you, the surroundings, are losing heat, and the system is sucking the heat in, so the system is gaining heat. That's what we call it a positive number. Okay, the rubber band, the best way to explain this is not the rubber band, but let's say a volleyball net or a tennis net. For any of you who've ever played volleyball, badminton, tennis, anything where you have a net, when the net is lined up on the two poles and stretched out, is it very organized? Are the squares perfectly square? Is it very tight and taut and you can throw something and have it rebound back? But as soon as you take it off those poles, does it stay stretched and organized? Or does it knot up and turn into a mess that's really hard to untangle? It collapses and it twists and becomes this knotted mess. That is entropy. The desire for that net to get all crossed up is actually what drives the rubber band to recoil. Because if it's endothermic, it'd rather be stretched, but because of the entropy factor. This is what they also consider for a lot of examples of any sort of macromolecule, that polymers would rather be randomly coiled than stretched out. So they would rather form intertwined chaos than the organized structure. So when we stretch it and organize it. When it relaxes, it goes to chaos. So this is a so-called chaos-driven process. Hopefully that makes sense. Okay, so this equation is key. And if somebody asked, what the heck do these circles mean? Other than they look kind of cute, they had a little charm to it. The circle means a special case. So how many learned circle meaning standard conditions? Perfect. Standard conditions would be 1 atmosphere of pressure for all components, 1 molar for all components, and 25 degrees Celsius. What it does not mean, and I really want to correct this, there was one lecture where somebody said it's 0 pH. Oh gosh, no. Please don't ever think that. pH would be 7 if it's an aqueous environment, but they don't define a standard pH because it doesn't have, that would imply there's always a solvent where H plus can move around. There is no defined H plus. But if it was in fact an aqueous-based solution, its molarity of the solute, the H plus would be standard water, would be pH of 7. So just for what it's worth, these are the things. 1 atmosphere for all gases, 1 molar for all components, 25 degrees. The reason it becomes an issue in biochem, just out of curiosity, is your body 25 degrees Celsius? I sure hope not. If it is, leave lecture, get to the hospital. You should come in around 37-ish, plus or minus. Okay, second thing, is every component in our body 1 atmosphere and 1 molar? No. And so the way you also see this from time to time, how many have ever seen this before? Does this equation look somewhat familiar? So here's, if you really want to interpret what this tells me, it's the following. The total amount of energy I actually get is what I would get if it's ideal, plus how much energy it takes to go from ideal to what it really is. So let's say it was actually at equilibrium or ideal conditions, then what is Q? If everything is 1 molar or 1 atmosphere, what is Q? No matter what, if all the products are 1, 1, 1, 1, 1, then 1 over 1 times 1, or 1 squared over 1, or 1 to the third over 1 squared, whatever it is, Q is 1. What's log of 1? 0. This term drops out, and it's just delta G would equal delta G naught under perfect conditions or ideal conditions. What we're going to say here, you know what? I got to use the real words, standard conditions. Delta G, what I actually get is a delta G if it was standard plus the energy associated with being deviated from standard conditions. So this is your actual energy. This is in an ideal world where everything was standard conditions. How many agree this is kind of a waste of time? This one? We just don't have those conditions. We like to make organized lists. And that's the whole reason this exists still, is because textbooks have massive lists of delta G naughts. But reality, delta G takes into account what it would give under standard plus what's associated with not being at standard. So when you actually look at a reaction in the body, which is more important, delta G naught or delta G? Which one actually is the one that, if you truly were trying to decide whether this pathway is going to work, you should look at? Perfect. Delta G, because it takes into account what the body is. No, exothermic means heat is released. Spontaneous means delta G is negative. So when we say exothermic and endothermic, which I think, oh, that's over here, that's talking about the heat. Delta G, favorable or exergonic, is a negative delta G. Unfavorable or endergonic is a positive delta G. 2 separate terms. No, you can have, this is a perfect example of, here's an endothermic process, rubber band stretching, going to relax, endothermic, but naturally favorable because of delta S. So because of entropy, we cannot necessarily make the statement that exothermic equals spontaneous. Now, there is a very high probability that if this is negative, this will likely be negative, or if this is positive, this will likely be positive, but still we don't know for sure. Yep, exactly. Delta G, H, and S to a chemist, and these are chemical terms, describe always what happens to the chemicals. So I think it's a really good perspective to keep in mind. What do chemists care about? Chemists care about chemicals. They only care about the system. And yep, exergonic, and this is what's so, well, okay, choose my words carefully. No, I won't. I'll choose it. This is what's just a pisser about chemistry. Do we have the same word or the same thing with 3 to 4 different words? Can I say exergonic? Can I say favorable? And can I say spontaneous? And I'm saying the same thing. And it's because there is chemistry throughout the world. And for whatever reason, one country chooses a word that might be different from another country. And because it's a universal language, rather than just getting one universal term and piss off a couple places that had their own personalized term, they just keep on letting too much language going on. So I don't know which one it is, but I do believe spontaneous might have been a mistranslation from way back when that they just stuck with. Spontaneous, whatever the original language that came up with it, really was saying something that happens, something that's favorable and can happen. And it just came across that way. So we have to know all these words. Oh, by all means, this is exactly the one. The most typical example, I think, where they will screw with you is protein folding. So they might tell you, for instance, that when a protein folds, it forms a bunch of H bonds with itself. Therefore, it's forming bonds. Bond formation is stabilizing, so that would be exothermic. But they might tell you folding into that conformation is actually unstable because of an entropy factor. So for just considering the protein, it may be a case where it is exothermic because it makes all these new H bonds, but it's actually endergonic because it's unfavorable because of the chaos that you've lost. You've lost from a linear protein to a folded protein. So that's a perfect example. This is exactly the example. Anytime we have a macromolecule, when it's stretched or organized to relaxed, going from ordered to disordered, that becomes significant. And so most of the examples where exergonic and endothermic would go together, or exothermic and endergonic, where it's crossed up, always has to do with the delta S. That's almost always the case of a macromolecule going to one state to another. And it can also be a case where you have a solid going to a gas. That's a drastic change in the amount of order. Okay, so making bonds is endothermic. You must put energy in. So if you think about two atoms near each other, if I want to move those atoms that are held together by some chemical bond away from each other, do I have to pull really hard on them, or do they naturally fall apart? To break a bond, you must put energy in. You must take your two hands, grab one atom and the other atom, and pull them apart. You are putting energy in to break a bond. So bond breaking is an endothermic process. And if I have two atoms that want to form a bond together, I put them near each other, they'll fly together, form a bond. That energy of them coming together is released as exothermic. So exact opposite of what's posted there. So making bonds equals endothermic. Oh, no, you wrote it perfectly. Oh my gosh, I'm so sorry. My eyes are so jacked up. I have to figure out how to make my chat bigger. Michaela, what you wrote is absolutely positively right. At what point did you realize I was going off the rails and wasn't able to read successfully what you put? Yeah, I mean, I'm saying the same things you are, but telling you're wrong, and that's so backwards. I'm sorry, you were 100% right. What you typed is exactly what I was trying to say. Breaking a bond, you have to put energy in. So break a bond is endothermic, making a bond is exothermic. Exactly what you wrote. Honestly, exactly what I said, but clearly what I didn't read. So sorry for my reading skills. I'm going to blame it again on LA Unified School District education combined with just being old and refusing to get glasses when I should. Okay, and then something that was posted up here also. Linear is more disordered than folded. Yes. So think of yourself. If you tie yourself up into a ball versus if you have your hands and legs flailing around, where are you more disordered? Flailing around or in an organized ball? So picture after like a chemistry homework, you ball up in the corner in that small little knot. That's very disorganized. You're locked in. But before you start, you're feeling happy and gleeful. Your hands are flying around. So the energy released when two chemicals come together is the bonding energy. So we define it as two atoms infinitely far apart, opposite ends of the universe, that somehow find their way and come together to form a bond. From zero attraction to complete attraction, maximized attraction, the energy released is the bond energy, the bond association energy. To break a bond, we call it the bond dissociation is break apart, dissociation energy, that's pulling it apart. It's not really, it's okay, if something was vibrating so much and broke apart, that would be the bond dissociation energy. So I'm going to stay away from vibration. Vibration is IR. So bonds aren't perfectly still. They do vibrate, but we're talking absolute, from far apart to coming together to their optimal distance. That's your bond energy. Okay, I'm going to click to the next screen. A lot of this stuff is all going to tie in. So keep your questions coming as we go through this. But this, again, how many would agree there's a certain amount of just terminology you got to get down pat? Just a certain amount of rote memorization of terminology. How many have already committed that that's your life? Memorize shit. That's just what it is. That's exactly what this is. Notice that I can say this multiple ways. Favorable, spontaneous, exergonic, delta G is less than 0. Delta G greater than 0 is unfavorable, non-spontaneous, and endergonic. And again, because it comes from many different languages where they define things, sometimes the way they said it translation-wise, these meant the same thing. They just, the thesaurus was crap. Delta H, exothermic, it feels hot to the touch because it releases heat. Endothermic, it feels cold to the touch because it absorbs heat. And again, you are the surroundings. You don't get to be with the chemicals. And then finally, entropy, delta S. This is one of those that, again, you just have to accept. When the world falls apart, do chemists think that's a good thing or a bad thing? Everything falling apart, they assign that a positive number, more disordered. Okay, so which part summarizes it? The fact that it's all chaos, it's hot and cold, or that they said the same thing 3 different ways? So, because that's a, yeah, but that's a beauty of the MCAT. It's how you look at everything and organize it to look at it, I don't know, big picture. Because again, although this is something we first learned in GChem, how many agree this pops up again a lot in biochem, a little bit in OChem? Yep. And it's just terminology. Honestly, what really bothered me, 3 words for the same thing. And we all have our little pet peeves, but that was one that's like, you, and then profanity, insert profanity here, chemists, but it is what it is. Stretch and rubber band, again, want to revisit this. From its stretch state to its relaxed state, it is totally natural. That's the way it normally happens. So delta G is negative because it is a spontaneous, favorable, exergonic process to go from stretch to relaxed, but it feels cold. This is one you just have to trust me on. How many actually pulled out a rubber band and tried this? Perfect. So perfect. Thank you. Elton, I was going to ask, did you find, it's not that it's super freezing, like you don't like get frostbite in your lip, but it's really surprising. And you're basically just using your lower lip as a thermometer. But yeah, it actually feels, you can actually tell that it is colder. So you stretch it, put it on your lip, let it come to equilibrated temperature of your lip, pull it away, let it close real quick, put it back in your lip as fast as you can, and it will feel noticeably cold. Weird, but totally true. So again, plugging in negative delta G because it's favorable, positive delta H because it's cold, meaning T delta S has to be bigger collectively than delta H, meaning number one, because you were subtracting it, delta S must be positive and it must be significant. So anytime I go from a stretched organized polymer to relaxed chaotic polymer, it is driven by entropy more than it is by delta H. And again, this concept right here was revolutionary. This literally changed the way people looked at proteins. Because how many learned that the Pauling method or just the idea of H bonding being so important in protein folding? How many learned that from your biochemistry books or professor? And when I was an undergrad, that was the prevailing theory. Hydrogen bonding, delta H was all that mattered. But this theory is called the Kaufman theory on this, where it's driven by entropy. Yeah, exactly. So, and that's the added feature into it. Notice I'm being polymer centric. I'm only worrying about this polymer. But you're saying, is there also a secondary factor where the water, whereas the protein itself, the polymer might be getting less ordered or more ordered, depending on which way I'm going? But you're absolutely right. Do I have to worry about water binding and being released as a protein folds? By all means. Different books call this different things, but how many learned it like something along the line entropy payment? Have you heard any variation of that phrase? And every professor might say it slightly differently. But entropy cost, entropy price, entropy payment, do these sound at all familiar from anything? So that's basically what this is. To carry out any sort of folding or unfolding and the water leaving or coming in, that bulk phase or the bulk phase perspective, what happens to the water on the whole, where the water gets more random or less random, is part of that whole, the entropy cost, the entropy price. So entropy plays a major role in protein folding. That's kind of what I'm trying to get at with this one. So rubber bands at the microscopic level, polymers at the microscopic level are like a net. When you let them go, they twist, tie knots, get chaotic, and that's favorable. Okay, Hess's law. And I apologize in advance because I have no clue if I've done that right. In trying to look at different books and different resources, I'm convinced nobody on the planet knows what's right or wrong. Yeah, it's a good question. And you know what? I apologize. I got a private message question that I'm going to totally blow off because you are living in the future. That's going to be one of the questions you run into, maybe even question one. So I totally apologize. So I don't mean to say I don't want to answer your question, but I don't want to give away the spoiler. Hess's law. How many learned that Hess's law says if you add a whole bunch of reactions up, you get an overall reaction? And if you do that, you can simply add their delta G's. You can add their delta H's. You can add their delta S's. What do you do for K equilibrium? Do you add them or multiply them? Perfect. Somebody already beat me to it. For this one, you multiply. It's the one weird one. K equilibriums, it's kind of because in an overall reaction, products over reactants, you want products on top, reactants on bottom. So this is ultimately the product here. This is the reactant we start out with. We want to make sure that's in the denominator, that's in your numerator in the end. Okay, so I'm going to erase this just because I need the room. But just to make note, for delta G, delta H, delta S, that's Hess's law. We can add them up. Erasing in 3, 2, 1. Gone. So how many learned about these sorts of reactions? Either a combustion reaction or formation reaction. Do those sound vaguely familiar from your travels through GChem? They give you the back of your textbook with a bunch of formation reactions, forming it from its most stable components, elements in their most stable state under standard conditions. And how many remember having to add up all the delta H's for the individual components and getting overall delta H for a reaction? Does this sound vaguely familiar? Certainly fair game on the MCAT. So formation reactions. I'm going to tell you that a carbon solid reacts with 4 hydrogen atoms in the gas state to form this. Is this a correct formation reaction, or is this a TGL moment? A little bit of TGL going on. What have I done wrong? So Michaela or Brooke, what do you recognize in my propensity to lie? Okay. Isn't carbon a solid? You're absolutely right, but something's wrong with it. So I want to go off on a tangent on a word called an allotrope. So is an allotrope a word you've heard before? So how many have heard it, don't know what the hell it means? That's a word that went in and was fleshed out right after the final, and as it should be. But if you know of a typical example, that'll help. Graphite, diamond, and Buckminster fullerene, known as buckyball, are known as allotropes of carbon. What is the difference between diamond, graphite, and buckyball? Configuration of atoms, exactly. In a diamond, you have everything sp3 hybridized, everything sigma bonded, all the carbons. In graphite, you have everything sp2. You have a massive, like, if you will, sheets of benzene rings connected to one another in both the y and x direction, stacked on one another. Buckyball, you have this soccer ball, basically, full of all carbons. So allotropes, so this one specifically, they're all solids, but be a little more specific. Okay, what other error have I made? So carbon has to be the specific allotrope. What else? How many agree hydrogen gas is the most stable or is not the most stable form? It's not. How does H exist? H2. So I got to change that H2 gas. I got to change that to the right allotrope. So it's 2 H2 gases and grr. It's kind of weird, but what is forever? Diamonds or graphite? Product of advertising. When they say diamonds forever, they're lying to you. They're giving that to sell you a concept. So if somebody were to give you a diamond in a piece of jewelry saying that they think what you share should last for a lifetime or eternity, don't settle for diamond. Demand graphite. Graphite's the one. Eventually, all diamond will convert to graphite, given enough time. So graphite says they care. Exactly. Here's a pencil tip. Yep. If you truly show love, if you love somebody and you're a chemist, a number 2 pencil says love more than a diamond. So next time you're out at that fancy outing and somebody has all these diamonds on, show them your graphite. Show them your pencil earrings, your pencil ring. Oh yeah, it's about 10,000 years for the edges to start to wear and turn to graphite. So yeah, I mean, probably a couple million years for it to completely convert. Yeah, okay. So maybe they last a little bit longer than your lifetime, but I still think if somebody gives you a diamond, it says they don't love you. By the way, today's lecture not sponsored by De Beers. Graphite is forever. Okay. O2, is O2 correct? Or is it O gas? I can't remember. O2, perfect. So we're good on this one. And then H2 gas, O2 gas, we're good to go. So these are called formation reactions, forming the molecule from their most stable component elements. But here's the catch. CH4 is on the correct or incorrect side compared to the overall reaction. Incorrect. Does that mean I need to reverse this one? Make it CH4 going to those 2 products. CO2 is on the correct side, H2O is on the correct side, but do I need 1 or 2 H2Os? I need 2. So this one needs to be reversed. Because I reversed it, it's now negative of formation of CH4 because it's flipped around. This one's fine, and this one needs to be multiplied by 2. So overall, am I reversing reactants or products? Yes, so Why is this a 1/2 and not a 2-1-2? It's always based on one molecule of what I care about. So because I want a 1 here, because I want to make 1 water, and it's 2/2, or sorry, 1 1/2 and 1 as opposed to 2-1-2. So does that seem okay? So every other time you're told don't put halves in equations, this is the exception to the rule because it's always based on one product. So it's based on, you can have halves. And again, it's annoying because do you agree the rules are, well, this is usually what we do, except when we don't. Most chemistry rules, there's always an exception. That's a weird sentence. There's always an exception except when there never is. Okay, so for this one, did I reverse reactants or products? Which one do I have to flip around? Reactants. Perfect, exactly. So let's make sure this works out. Graphite cancels, check. H2s cancel, check. O2 doesn't cancel both on sides, so I need 2 of them. So cancel out H2s, 1 CH4, 2 O2s, 1 CO2, 1 water. Perfect, adds up beautifully. So I keep formation of products as is. I make a negative for reactants. Somebody learned this. It's delta H formation of products minus formation of reactants. Products minus reactants. And so I want to take a moment and just share with you, if 2 people are in love, how many have ever heard they have good chemistry? How many have heard people use the word love and chemistry synonymously? Yeah, it's just the way it is. The reason it's this way is because chemists represent the ultimate pinnacle of love. Chemists love you. So much so that did they make everything in chemistry alphabetical? Is it products minus reactants or reactants minus products? Products minus reactants. Is it bonds broken minus bonds formed or bonds formed minus bonds broken using the alphabetical rule? Broken minus formed. Absolutely perfect. When it comes to the gas laws, I'm going to go off on yet another tangent. ABC, Avogadro's law, Boyle's law, Charles' law. Every one of them studied volume compared to, what are the other variables in PV equals nRT? Do you agree? Pressure, moles, and temperature? Which is first alphabetically, moles, N, pressure P, or temperature T? So Avogadro studied N because first alphabetical. Boyle, ABC, second alphabetical. What did Boyle study? Pressure. Charles, got to choose third alphabetically. Is everything in chemistry alphabetical for your ease and understanding? When in doubt, make it alphabetical. It is amazing. How many are sitting there thinking sort of dumbfounded like, crap, that's true? Pretty nifty and convenient way to remember things. They already made it convenient for you. So for thermodynamics and gases, trust the alphabet. They made their laws. In fact, there were other professors or other theorists that had letters, alphabet names beginning with D through Z. They wouldn't let them submit. They said, get out of here, dang it. We're taking our good friends A, B, and C, Avogadro, Boyle, and Charles. Do you believe my story? Yes. Thank you. Elton is favorite student. The rest of you, not even close. You're chasing Elton the rest of the way. Products minus reactants, perfect. So if it's okay, I'm going to click. We're going to do one more thing, and then I'm going to throw a couple questions at you. In the start of a reaction, do you break bonds or form bonds initially? Generally speaking, you have a leaving group leave or nucleophile come on, or possibly both. Have to break a bond. Something has to leave. So we invest energy. Broken. So bonds are broken early in a reaction, but they're formed later on, so we get energy coming back out. Delta H from start to finish, if I put only a little bit of energy in, so I'm breaking weak bonds, so a small positive number for input, but I'm forming strong bonds. That's a large negative number for output. So small positive number input, large output. So overall, would you get energy in or out? If you put a little bit in and get a lot back out, overall out. So exothermic, the way it works. Again, broken minus formed. This is a positive. These are negative. So broken minus formed because you get a negative for that. So an exothermic reaction, you're breaking weak to form strong. So I want to put this to the test by looking at something we know from biochem. What is this representing? I haven't drawn the whole molecule out because it just didn't have enough room. But what am I representing by this and this? Hydrolysis, perfect. I'm using water to break some bond. And what am I hydrolyzing? Somebody already put it. Perfect. This is ATP. This is ADP, inorganic phosphate, and water. Okay, you're going to hear my iron disdain for biochem terminology as well, and that is this a strong or weak bond when you have all these negatives nearby? They want to attract one another, repel one another. It's weakened. So even though they call it a high energy bond, it actually has a very low bond energy. So it's a high potential energy bond is the way they probably should put it. But this one is a weak bond. So let's consider what we form and what we break. We break this bond here, and I could have chose either one. I've chosen this one because it's easier for water to attack a terminal phosphate instead of internal. It's going to break that bond. And again, it could be either side. I don't care. Yeah, why they call it high energy is because they say it's high energy that you get out of it. You get energy out of it. So it must start at high energy and must form down the road. It's just a misnomer. So how many have ever heard it's high energy bond? They really should say high potential energy or high in the energy diagram because it gives you energy coming out the other side. So by all intent and purpose, it's actually a weak bond because of the negatives repelling one another. Negatives repel, it stretches the bond. Longer bonds are weaker bonds. But it doesn't matter to us anyway because the energy associated with this is for one bond or the overall process. Overall process, exactly. Broken minus formed. So if I break and form, so notice I break an OP and form an OP, and I break an OH and form an OH. So at face value, am I breaking the same bonds I'm forming? So first thought is delta H should be 0. However, did we just conclude this is a little bit weaker than expected? Because that negative repulsion, this is a little bit weaker. So what's going to be true? If I break weak to form stronger, what's happened? Yeah, it's basically because this OP bond is weak. It's this OP is better than this OP. OH is kind of a wash. It's the OP. This is a weak OP. This is a stronger OP because of less repulsion. So overall then, we break weak to form strong. So is it true that hydrolysis of ATP, converting it to ADP and inorganic phosphate, how many learned at some point that this is in fact energy releasing? I mean, this is probably totally new. They probably never mentioned this in biochem, but you actually can store energy as ATP. How many heard such a crazy thing? Pretty much all the time. So hydrolysis of ATP gives us the energy, not breaking the bond, but breaking two bonds to form two more stable bonds leads to the energy released. I learned it as negative 7.4 kcals per mole, but in most biochem books, do they give you calories or joules in your travels? Kilojoules. How many learned this as about negative 30 kilojoules, roughly? Does that sound vaguely familiar? Joules and calories converted by 4.18. So negative 7.4, what I learned in calories times 4.8 is around negative 30. Does that sound about right? in the ballpark of what you've been taught. That ATP is about negative 30 kcals per mole when you hydrolyze it. Kilojoules, excuse me. So I'm going to toss that in there, and I hope that sounds familiar. How many does it not sound familiar at all? So for the most part, were you just told to look at numbers and make decisions how it goes? Or will you learn, I mean, how many learn negative 7.4? Wow, with nobody responding, I'm really starting to get nervous about my numbers. So let me erase that, then ask you, does negative 7.4 sound at all familiar? Negative 7.3, 7.4, does that sound vaguely familiar to anybody? For delta H? Okay, so negative, okay. Okay, so perfect. So this is kcals per mole, negative 30 kilojoules per mole. And yeah, then again, it might be that the professor just didn't care about what numbers and you just figured out in context, which is fine as well. Toss a number there because we use it as such an energy molecule. Okay, so 3, 2, 1. Oh, sorry. Let me get rid of everything I have in the way. Okay, so for this one, break weaker to form stronger, lower number minus bigger number, overall negative. So this is overall negative because this is abnormally weak. I don't think you need to memorize most numbers, but I think it actually might be worthwhile to know ATP. I don't know why, because when I think about it, I'm scanning my memory. I don't think anybody's ever come back and told me they really wish they would have known that number. I think just because it's so common in biochem that it doesn't hurt to know it, but I honestly don't know if yeah, I'd Anki it. But honestly, my core thought, if I really work through it, I don't know if it's important to know. I just want you to know it, damn it. So I apologize. I'm guilty of that at this moment. Okay, couple questions. The first one is going to be one that was suggested earlier. So I'll give you about 30 seconds to a minute. Okay, so got some answers submitted already. So I'll go ahead and figure out what the heck's going on. So can I just look at the table and look at the del test directly to figure it out? So how many can read the del test right here, already drawn out for me? Does it show up on your screen?
No, I don't see.
Yeah, okay, so I'm lying to you again. Crap, there is no del test table. I got to make my own. Okay, I don't care what it is numerically because they didn't give me a temperature, but can I at least figure out what it is sign-wise? So I think delta G equals delta H minus T delta S. So let's just figure it out. If this is plus 44 and this is plus 42, I'm going to ignore the points. What is this overall value then? How many a negative 2 because 42 minus a minus would be plus and equal that. So if delta G is bigger than delta H, then it's a negative number. And again, is this bigger than this? Sure. So that's a case where this must be a negative number. And is this bigger than this? No, this one is more negative. So I actually want to write that in there. More negative, which makes this a positive number. Does that help me at all? So what is true if something experiences an increase in disorder? So let me get organized here. An increase in disorder is defined in terms of what for delta S? Delta S is positive for an increase in disorder. So for an increase in order, delta S would be, actually, let me do a different color. Increase in order, delta S would be a negative number. So which one is it then? Perfect. Is this a hard question, not because the concept or the equation are challenging, but because that's a hell of a lot of work and lots of careless errors by looking at numbers that are weighting it. So the question is, did I make it easy or did I just go through it systematically, step by step, and not panic? Hey, any mnemonic works. Goldfish tastes horrible without tartar sauce. I like it. Okay. And I think panicking is, and this is one of the things I love, seriously, I cannot tell you how much I love that being very candid about what happens during these questions, because is that how you get better? And I'm going to open up about something that probably each one of you, when I say this, that emailed me is going to probably be pissed off that I'm saying this. But of late, I've had a lot of people email, this is how I'm scoring on a phase 2 or a phase 3 and going through panic mode. And the thing that a lot of you have done, and some that I suggested, some that just did it naturally, said, but if I could get rid of careless errors, if I could get rid of just brain farts or whatever word you used, how many notice your score is significantly higher? How many notice your total you get right goes up by 5 to 10 out of 50 or so? That's the growth that you have to worry about. Your knowledge, you're going to increase it. You're going to get some more information. That's going to help a little bit. But more than anything is getting those panic moments under control and keeping focus when you are getting really fatigued. Yeah, and exactly. Is this real easy to misread everything? And the other thing, you said it looked easy, but let's also be realistic. I gave you enough time that I could walk outside, look at the mailbox, come back in, say, oh, it's all crap junk mail, and sit back down. 40 seconds. It took me 2 minutes to go over the whole thing. Unlimited time, this is an easy question. Under time pressure, it is not so easy. Yeah, and you nailed it perfectly. That feeling of given enough time, I can get things right. And in the moment, you know what? We're all going to panic. How do you recover from panicking is far more important than trying to alleviate panic. It's going to happen. Yep, and that's the thing. How many agree with Ninika's statement? And that's, I mean, you're going to miss things here and there for other reasons, but how many would agree the pressure actually does, I mean, that anxiety does cause a negative impact on your results? Yeah, Leandro's tip is one of those suggestions that definitely make. How many notice when you start writing stuff down, it helps you to calm down, it slows you down? Anybody ever notice that when you start to write notes to yourself, it makes you more organized and it makes you calm down and go slower, and it makes you individually do the steps. Yeah, try doing that on questions that bother you, especially when you redo the question second time after you get it wrong. Yeah, see, I agree with what Elton said, except for one thing. I'm the slowest reader on the planet, and I don't have time to write, and I really wish I did. So, and if you can afford the time, more power to you. It's so helpful. Okay, I'm going to erase everything I wrote here and let the computer make it a prettier scheme. So erasing in 3, 2, 1, done. And go through the same thing. So an increase in order equates to a negative delta S. First thought. Based on the equation, delta G is delta H minus T delta S. This is only going to be negative because minus and minus be positive. So delta H overall plus some number would make delta G greater. So negative delta S leads delta G greater than delta H. That's what. Yeah, actually, I want to address that because basically you just nailed something that I think is really important. How many would totally agree with that same thing? That it seems like note-taking, writing a lot of stuff would waste time, but actually panicking and spinning with your wheels in the sand, that's where you really waste your time. Yeah, last time I took the MCAT, you could highlight and you could strike through, and that was it. And at least when I took it, there were no shortcut keys. How many? Okay, it's still true. What about shortcut keys? Somebody told me that there are some. Okay, so yeah, and for me, just clicking the cursor down, dragging it, and lifting it up, honestly, was just better for me. Oh yeah, there's no search function. Not that I know of. I sure couldn't find one. But let me tell you, when you're sitting in that waiting room before you go in and everybody's standing around, you need to whisper to the person next to you. I can't remember. Is it Command F4 or is it Windows F4? What do I push to get the search function? Because what's a keystroke that shuts your computer down? That'd be so evil. You'd get beat up at lunchtime for doing that. But is it Alt F4? Okay. Yeah, I think you need to ask them that. Can you search for clues in the MCAT by hitting Alt F4? I'm just joking, by the way. Please don't do this. Oh, shoot. Let me click this up so you can click through. Yeah. Yeah, when I say things like this, please don't take these as serious statements. So if at some point I tell you to use super glue to make, click real quick because it's about to, I think I power pumped. If I tell you to use super glue to put a smiley face on your thumb and then tear it off, and then that'll permanently become part of your thumbprint. So that way when you take your thumbprint or fingerprint, they're all smiley faces. Don't do it. I'm just joking. Okay. I'll be quiet. This time I'll give you a true minute or so. Okay, so math. Oh, the feels like a trap one? We'll see if it is. Are the numbers spaced far enough apart that we probably don't have to be really anal about how we calculate? They're pretty far apart. So let's figure out what I need to do. I need to take reaction one as is or reverse it. As is that true? Combines reaction one and reaction two with the reverse of reaction three. So don't I take these two as is and then reverse that one? So is it really as simple as adding all these up? It's already columnized for it. Is this about 100? Is this negative 170? This is about 40. So 40 and 100 is 140. Minus 170 and positive 140. What's your guess? Around negative 30. Perfect. So mathematically, this is how I show all my work. Yeah. Are you know those curve busters who set the curve at the high end? I got to admit, there were so many cases because of careless errors. I was the other way around. I was the supportive part of the curve, because if anybody could make a dumb careless error, I was the one. So if you got B, you're on it. Because it's natural, because that's one of the things we do. But this is a case where reaction is a product of reactant or both product and reactant. Reactions, you just straight out add them. This is Hess's law. Add up the delta G's or delta H's or delta S if we had them for different reactions. Okay. Okay, so for this one, let's see what you're getting. So got another B vote. Okay. I might try to reverse engineer it at first. Are there typical mistakes that somebody might make? So in this case, is this a product minus reactant one? Okay. Do I need to multiply or no? I can't remember. I don't think I need to, or I definitely need to. I definitely need to. What's the one and only time you don't need to multiply? Voltages. Voltage is the one you don't need to multiply. So do you how remember E, like E reduction plus E oxidation, or E cathode minus E anode? You don't multiply in this one. So in this case, I got to multiply. So 2 times that number or that number. Which one? So 2 times 240 minus 3 times 200. And again, I'm just being completely bad at my rounding. Am I still okay? How much pride? Zero. None, nada. I have no pride whatsoever. I don't care if I'm doing math so poorly, because is it still good enough to get me a right answer? So do they have answers in there if you did the wrong number minus the wrong one? And do they have wrong answers if you forgot to put coefficients? So is 238 minus 205, is that around 33? Negative and positive versions. And then when you multiply, 138 versions. Hey, it's not a rookie mistake. It's a veteran who hasn't done it for several years mistake. That's just what these things are. Nitpicky crap. And I want to address something. All of you expect perfection of yourself. Wait till you're a doctor to put that much pressure on yourself. For now, it is okay to make a mistake and learn. Okay, so the question popped up. How do I know if it's products minus reactants or broken minus formed? Because in this case, do they give me products minus reactants in terms of the terms for it, or do they give me bond energies? Okay, so what are they actually giving me? Are they giving me bond energies? That'd be broken minus forms. Or are they giving me S's? So the only time you use broken minus formed is bonds broken minus bonds formed. So if they give me bond energies, that'd be perfect. But they didn't. They gave me S's. So when they give me H's, G's, or S's, so they give me enthalpy, entropy, or free energy, then I use products minus reactants. So it's, and would you agree, the hardest part of questions like this is figuring out what in that massive pool of things you know is applicable. So your question, what do I use, is perfect, because how many have to go through that every single question? What did they give me, and therefore what fits? And how many struggle with that all the time? Okay, so what it was is they gave me S's. There's two equations, broken minus formed. Yeah, so when would you use that? When they give you bond energy. So they said this bond has a certain energy and this other bond has a certain energy. Then I would do bonds broken minus bonds formed. But if they give me just H, G, or S, just straight enthalpy, entropy, or free energy, then I have to use products minus reactants. I would have to just look at the reaction itself. So how do we know in that one example, ATP hydrolysis, we had to actually look and physically see which ones were formed and which ones were broken. And then you can look it up. So for instance, this is a really good example. So that's a case where they're showing me bonds. So this would be bonds broken minus bonds formed. What are the ones we break? We break an HH. We break the double bond, the pi bond. Or let me, actually, the way we do it, we break a double. And we form two CH singles and a carbon-carbon single. So this would be formed and formed. This is broken and broken. So does that make sense that if they gave me a reaction and I can look at what, oh my, I'm so sorry to laugh because it just sounds so much like a Dr. Seuss phrase. Oh, I do not like that. I do not. And having gone to a school where Dr. Seuss was like our major donor, that's always what we used to joke about. We always used to speak that way. UCSD, woohoo! Yep, Triton I am. So in this case, what you break, what you form. Broken minus formed. So you look up the energy for that double bond and that single bond there, add that together, and then subtract the energy of a CC single bond and two CH single bonds. That's a different question. So this is a what if we did this different? Okay, I'm going to erase this because I don't want it to be part of this solution. So getting rid of it in 3, 2, 1. So for this one, same thing. 2 times 240 minus 3 times 200. So there is your precise answer, which how many, when you see the precise answer, say, nah, not necessary. 2 times 240 minus 3 times 200 was close enough. If you like precision, wait till surgery school. For now, just get the answer quickly. Okay, one more question out of this grouping. So 3, 2, 1. Yeah, surgery school comes after doctor school. So you first go to doctor school, and then if you're good at doctor school, then you go to surgery school. Perfect. So for this one, tell me about the enthalpy first off. When I go from a gas to a solid, am I going from high energy to low energy? So is that releasing heat? So what's delta H for that one? Negative. Perfect. And tell me about entropy. When I form a solid, have I become more ordered or more disordered? More ordered. So therefore, I have lost chaos, lost randomness, lost disorder. So that is bad. That'd be a negative delta S. So best answer, D is in, dang, I think I got that. So is this a question of just, do you know your sign conventions? Let me erase what I put up here so I can have a prettier version for your screenshots. 3, 2, 1, clear. And so for this one, gas molecules are more random than solid, so therefore delta S is negative. And then when you go from high energy states, such as a gas, into a lower energy state solid, you're releasing heat energy. Delta H is negative. Best answer, D is in. Dang, that wasn't so bad. Okay, the next part, I'm going to sort of blow through a little bit faster. This first part, I wanted to go slow because these questions show up with high frequency, what we did to this point. Yeah, so good question. So when these things go from gas molecules that are free moving to suddenly interactive, are they forming intermolecular bonds? Which very much are like bonds. So when we form bonds, formation of bonds is energy releasing. Yeah, that's a perfect way to say it. So exactly. So intermolecular forces are still bond-like. So spot on. Definitely. That's a great way to look at it. Is that how you did it as opposed to some energy state perspective? Perfect. It worked beautifully. Once again, proving, are there multiple ways to answer every question? And one way is your best way as opposed to my best way. I love that. I love when somebody has a different solution that's just as viable, just as solid, and just as good. And thank you for chiming in, because that is actually probably a better way to think about it. So very cool. Okay. What's the difference between H and Q? Oh, yeah, that Q. Yep. So delta H takes into account from bonds. Q can involve heat loss and heat gain due to, let's say, the world around you heating you up, breaking you down. So Q is all heat gained or lost. H is just heat gained or lost from bond energy. Yeah, so perfect. It's a really, really good, solid way to think about it. Okay, calorimetry measures the heat associated with something. The one equation you have to know, which I just don't know how you can memorize it, but the total heat gained and or lost by a system, I believe, it depends on the mass, depends on the heat capacity or specific heat, and it depends on how much the temperature changes, but I just don't know how to memorize that. Yeah, this is going to be on the MCAT. Good point. So see how somebody typed that in, said this is an MCAT thing? Yes. But yeah, again, Elton, it's going to be on the MCAT. I get it. You guys quit telling me. I know it's on the MCAT, but how do you remember it, damn it? I'm sorry, it's just so wrong. But yep, how many agree? That's one I kind of know. Come on, seriously, exactly. You tell them, Leandro, yell at them like me. Okay. Okay, so within that, perfect. So Q equals MCAT. So what does Q represent? This Q we're talking about represents either A, heat released by a reaction, or B, heat absorbed by the system or the surroundings or whatever it might be. So is it true that energy is conserved? Sure. So the heat released by a reaction equals the heat absorbed by the surroundings, or the heat absorbed by a reaction equals the heat lost by the surroundings. Both things, exactly. Q gained equals Q lost. Q gained by the surroundings equals Q lost by the system, or vice versa. So that's what we're gonna get at. So if I mix a strong acid and a strong base, how many learned that if you add acid to base, the flask gets kind of warm? I mean, how many have ever mixed it and started to pick it up and like, ooh, ow? How many just don't really pay attention to those things? But if you did, strong acid, strong base, highly exothermic. Okay, so we have the following. We have a thermometer. Thermometer should be centered, and I put it near the edge. It should actually be here. We stir it so that it's evenly distributed. Insulated double cup, because when there's an airspace between here, is it harder for heat to transfer? Heat moves through the system, then it has to go through convection through the solution, conduction through the walls, convection through the space, conduction, and then outside of convection. The more space you have, the harder it is to move around. So, Alejandra, would you mind, or Alessandra, would you mind letting in Marissa? I can't move my cursor. Oh, you know what? Actually, my cursor is good to go. Thank you. Sorry about that. A lot of pressure on you, huh? Okay. Do you remember doing this reaction in lab? Yeah, it's a tough gig. So do you remember you took a temperature, measured, and then you mixed them and the temperature shot up? So if you remember this, we mix it together, we test it, then we mix it. If it's exothermic, what should happen to the temperature of the solution? Goes up or goes down? If it's exothermic, the chemicals release heat to the water. The water heats up. So we're going to see it shoot up instantly because the thermometer instantly reads and reactions occur instantly, or does it take time? It takes time. So the reading's going to go up a little bit at a time. So I might see a reading here, and here. Once it gets here, then it starts to go down. Why is it going down? What's happening there? Heat's being lost in the environment. Apparently, this is not a perfect system. Heat can escape through the top. Heat can escape through the walls. So unfortunately, you're losing heat. So is that just part of life? Will things cool down over time? How many got hot coffee a couple of weeks ago and it, fortunately, it's not hot anymore? Okay. So I'm going to make a couple suggestions. I say, let's just take the highest point straight across and use this for delta T. Yes or no? We don't do it because here's our concern. If it's losing heat at a certain rate here, was it probably losing heat there as well? So did heat loss just start here, or was heat loss going on the whole time? For this graph, I bring it back. Anything that's happening over time, we bring it back. That's my final temperature. So I forget, is this an extrapolated point that gives me something extra beyond the data range? Or is this a interpolated point that is within the data points? I can't tell. Is this extra or extra? One of the questions from not so long ago that they actually asked, which is a more accurate value, an interpolated or extrapolated value? Weird sort of lab question, but totally valid. Is it better to have 2 reference points because it's part of a trend? Oh, Elton, you have seriously summed it up perfectly. Yeah, that is true. The one I totally made up, this one is not very good because is there a chance the trend can change? Interpolated values, because you have 2 reference points and it's following a trend, always beat extrapolated. How many would agree what an obscure Cars-esque type of question to have in the middle of your science? Yeah, it is kind of a rude question, but the thing is, the MCAT, as you know, is about experiments. So some crazy person wanted to know which data point was better, the extrapolated or the interpolated one. And so just recognizing you get better data points here than when you extrapolate them. Word to the wise, because here I'm suspecting this happens, here I know for sure it is happening. Okay, with that in mind, I have a delta T. Delta T is around 10. I have an M. The mass of 100 milliliters, 100 milliliters is 200 milliliters, and their densities are around 1 because they're water, they're a little bit higher. So it might be a mass of a little over 200 grams. Heat capacity, water has heat capacity 1. This is actually salt water because there's ions in it, so it's slightly higher. So it's around 204 grams, let's say, around 1.02 in delta T. If I did 200 times 1 times 10 and came up with 2 instead of 2.14, is that good enough? Oh, how do we know it's 200 grams? Good question. I have no clue. So can somebody tell me if there's any way to recognize this? Oh, nice. Quick on the draw. Thank you, Alexandra. So they didn't give me grams, they gave me milliliters, but what is the solution mostly? HCl or water? Mostly water. What is the density of water? 1 gram per centimeter cubed or 1 gram per milliliter. So if it's 100 milliliters, is that roughly 100 grams? So it ends up, it's a little bit denser than that. So it's actually a little bit more than 100 grams, a little bit more than 100 grams. But that's where the 200 plus a little bit grams comes from. Yeah, the solution is water. And you have to memorize, what is the density of water? One gram per cubic centimeter, or if you will, 1 gram per milliliter. So 100 grams of water is approximately 100 milliliters and vice versa. So because it's not pure water, but it's close, I'm going to say that this 100 milliliters is about 100 grams. This 100 milliliters is about 100 grams. Altogether, I took 100 grams of one, added 100 grams of the other for 200 total grams of water surrounding the system. So does that make sense where it came from then? Yes, exactly. So what does AQ mean? Sorry to get all excited. I should calm down. Why, yes, that is true. Aqueous, water-based. So perfect. I just accepted my geekiness. And again, I'm probably, telling way too much personal information, but marrying a chemist was the best move I could have ever done in life. So, yep. Yep, exactly. The fact that it's aqueous, because if I have 1 mole of HCl, that's about 36 grams. That leaves about 1,000 grams of water in that system. It's definitely more than that. Oh, you think I should and would have, but no, I succumbed to the De Beers ads myself. So yeah, so okay. So maybe I lied a little bit. Oh yeah, it is a good thing. But you know, the beautiful thing is she wouldn't care at all about a diamond. There's so many more important things. So I'm impressed beyond belief. But solution must be stirred. Why? Because if it's shaken, it spills. That's so stupid, but it must be stirred to make sure water moves around, get even heat distribution, get circulation. Otherwise, you get hot pockets. Should it have a lid? Yep. If it's 5 molar, it's going to be a little less, but still, even if it was 5 molar, 5 moles of this would be around 150 to 200 grams. That still is 800 to 1,000 grams of water. It is still mostly water. So AQ, even in an extreme concentration, still it's mostly pool, not additives. Yeah, perfect. So would a lid be important? And really, this is a weird question, but if you are really cold, what is more important, putting on socks or putting on a hat? They're both important for two different reasons. Weird as it may be, a scarf and a hat are better than socks. Why? So socks help because it insulates. You're actually better off standing on a box on top of a surface and getting an airspace, but heat rises and you lose more. How many have learned if you want to cool somebody, you put ice packs on their carotids? I mean, how many have learned that as a first aid thing? Really? No, it's just one of those things that if somebody's overheating, you put it. Armpits get hot because they trap heat in there, but you don't lose a lot of heat there. That's why they get hot. So actually, armpits, conversely, they sweat a lot because they overheat the most. So you actually don't lose heat from your output or out from your armpits. Yeah, that's what I do. I pass out carotid ice cubes. But seriously, you haven't seen that a cold rag on a neck is one of the best things you can do to help cool people? You know, actually, Marissa's right in that sense. Anytime you can cool the blood, but the carotid supposedly because heat rises, and that's an accessible vein or artery, I should say. But yeah, actually, the back of the neck all the way through that vein, and I guess the carotid is really close to the front. I never even thought about that. I was going to say the carotid is, yeah, but it is, you're right. So if you wrap around, but anyway, nobody's ever heard that a muffler, a neck scarf, and a cap help you retain your heat. Huh. Okay. Yeah, report back on that one. Most of you live in cold environments too. So not to be disappointed, but I'm disappointed. Yeah. Yeah, putting on a hoodie helps so much on a hat. I totally agree with that. Yep. Okay. What would be expected if the concentrations were cut in half? If you cut it in half the molarity, half the reactant, half the delta T. Okay, why is heat capacity 1.02? Same reason why this wasn't exactly 200, because this weighs a little bit. Adding salt to water makes it absorb heat a little bit more. So in other words, the ocean can absorb more heat than a lake because it's salt water as opposed to fresh water. So is this pure or is this salt water if I have ions in it? Impurity? Salt water. If you put a 1 in there, would it really matter? So I'm being totally anal making it 1.02, but if you put a 1 and a 200, you agree you'd get essentially the same answer. So this is being anal, being precise, and saying the number I came up with, 2.14, instead of, let's say, 2.0, same old thing. And everybody read what Jonathan typed, because how many, based on your experience on the MCAT, would agree? They may give you exact numbers in a passage, but answer choices are always generous. There's always room for mathematical creativity on their answers. Yep, 48 rounds of 500. 42 to 40. Totally agree. Heat capacity, memorization, just pure memorization. The definition of a calorie is the amount of heat needed for water. So heat capacity for water equals 1 calorie per degree Celsius per gram. That's a definition. That's how we define it. We define this temperature scale based on water, boiling and melting points, and we define all other thermodynamic values based on water. So 1 calorie per every degree Celsius gram. Could I put this as K, by the way? And would it make a difference? Delta T in kelvins or Celsius, same thing. And good question. Do you get initial and final? You had to read it from the graph. It came in around 24. So that was initial, and you extrapolated out to around a little over 34. So yeah, T initial and T final were pulled from the graph. Yep, exactly. Although technically this is true, but what is the difference? So basically, I want you to do the math for me here. 34.4 minus 24.1 equals, and then so if I did it in C, oh, I didn't just do that. Okay, I hit the wrong thing. I totally panicked, sorry. Which delta T is different? 34.4 minus 24.1, 10.3, 10.3. So delta T, whether it's in Kelvin or Celsius, I'll count the same. Okay, last time I'm gonna, oh, you're confused how we got 2.14? 2.4 is just multiplication. 204 times 1.02 times 10.3. So 204 times 1 and 10 would be 2040. These numbers here, that's just multiplication on this one. And perfect. 200 times 1 times 10 would mean it's around 2,000 calories or 2 kcals. So this is just precise calculation as opposed to the other one. Oh, no. Oh, no. So C is that number. So that's my C right there. So that's my M, that's my C, and that's my delta T. Okay, moving on. Okay, I'm sorry, Brooke, you were saying? Oh, shoot. Okay, here we go. Oh, the final temp? It's because what happens is over the course of the reaction is occurring and you're getting all these data points as they come in, but this is not a perfect system and heat is escaping. So I watch this trend and I'm seeing, okay, I keep on losing heat. So at the time I mixed it, if the thermometer could instantly read it, and if the reaction occurred instantly, then I probably would have gotten around there. So we extrapolate to simply say that that's where we believe our final temperatures coming in. Okay. So let me see. I've totally missed your question. I apologize. I'm scrolling back up. Oh, heat capacity, specific heat for the MCAT. And if you're taking a physics or PChem class, you would be laughed at for this. But for the MCATs, it simply is this: specific heat is being specific. It's heat of whatever object, fluid, whatever I'm looking at, divided by heat capacity of water. So this is roughly 1. So a number divided by 1 is just that same number. It's just unitless. I'm going to use them interchangeably. So specific heat capacity, and heat capacity, I'm going to use like specific gravity. I'm going to use them all completely interchangeably because it really comes down to how you're measuring it in a constant pressure system, constant volume system. And so it's kind of a truth in advertising how I'm using my number. For the MCAT, MC delta T, I may call C specific heat one time, might call it heat capacity another time. Anyway, I'm always going to give it units and always going to call it ultimate heat capacity when I calculate. So I apologize for not seeing your question earlier. But for the MCAT, I'm going to say they are all one and the same. We're going to use them all. We're not going to be nitpicky about where one applies and one doesn't, because that's beyond the scope of what they ask. They just want you to throw a number in there. So hopefully it seems okay. I know, and thanks for looking out for each other. Again, I know I say this every time and it's getting sort of cliche, but it is so awesome that you guys do this for each other. I mean, it's seriously just, it's just a good vibe. Medicine's going to be in very good hands because of you guys, because I'm sure your attitude will permeate. Karma Pharma, I like it. Heat transfer, different ways that things get from one point to another. How many learn that high temperature gives away heat, cold temperature picks up heat? How many have learned this in life? You want to cool down, surround yourself with cold. Want to heat up, surround yourself with warm. How many discovered this at a pretty young age, probably called birth? You couldn't really control your environment, but somewhere around then. So heat naturally flows from a higher temperature object to a lower temperature object. That is natural heat flow. Can we get unnatural heat flow? Can a refrigerator take heat from a cold internal environment and squeeze it out and put it out the backside? But to do that, does it naturally occur? Do we have to do work? So is the refrigerator basically stealing the plan from a sodium-potassium pump? You get an imbalance and unnatural charge distribution by working on it. You get unnatural heat distribution. So hopefully it seems okay. Okay, so heat naturally transfers greater delta T, the faster the heat transfer. How many learned that and just in life? You touch something hot, it burns you. Touch something just a little bit warmer than you, it doesn't give you as much heat. Again, how many have learned this? Fire hot. So these are life lessons that you've probably got. Fire hot. Touch something really hot, burns. Touch something barely hot, not so much. Touch something super cold, same thing. Okay, so a couple ways you can move heat. Conduction junction, what's its function? Transfer heat through direct contact, thermal gradients. But solids conduct heat, convection, fluids. Convection, heat is transferred by collision. One hits another, hits another. It felt like it burned, but throwing up, doesn't that feel like it burns too? Yet fire is not acid. So the reality is our nerve sensations. How many learn that just overstimulation of your nerves generates the same sensation? Move hand. So extreme cold, extreme hot, both say move hand, bad. And so same sort of things. I think it's just excessive nerve stimulation, but different end result, frostbite versus a burn. Okay, radiation, is that how sunlight sends energy to our planet? How many learned that it gives off this radiation, travels through the vacuum, which means this one works pretty well. But this is the, I think, most interesting one. Is this how we heat and cool ourselves? And I don't want to make stereotypes, I don't want to judge, and I don't want to put you on the spot, but are there any of you who have once sweat like perspired in your life? And again, I'm not going to make any assumptions, but I think we know who you are. Okay, so one person has confessed. Okay, yeah, literally never. There's a few I know who've never done sweat just once, and that's fine. Experiment, peer pressure, all that. Yeah, in college, those experimental years, I tried sweating and it seemed okay, but yep. Why, for those of you who chose to sweat, why'd you do it? Yeah, just cold-hearted. Why would I sweat? Peer pressure, probably. Yeah, everybody's sweating, everybody's taking drugs. Let's do it. Okay, to look cool. These are all excellent reasons. What I'm actually looking for, though, is thermoregulation. Thermoregulation is the correct answer here. Although peer pressure and drug use are excellent things, don't get me wrong, but perfect. So you evaporate because when you have a thin layer of skin or thin layer of moisture in your skin and it evaporates away, what happens? You cool down. Perfect. How well does that work if you live in a very humid environment? So this is so cool that we have the full range of people's locations. How many have ever ran in the summer in a humid environment, like the Northeast or whatever? No. Why do you hate it? Why does it feel like death? You stay hot. Why? Why? Because unfortunately, when you sweat and it evaporates away, is there moisture in there that condenses back down on you and you break even? I've heard Singapore is a bit stuffy sometimes a year. Okay, so here's a weird question, medically related. If somebody is having a heat stroke or heat exhaustion, somewhere on that spectrum, how many have heard you should, number one, put them in an air conditioned environment if you can. Number two, douse them with cold water, cold solid, like ice, because ice will melt and you don't have to worry about evaporation. But how many have ever heard in a pinch, you can put rubbing alcohol on their neck? Is this something you've ever heard of? Why? Why would, not why haven't heard of it, but why would that actually work? It's actually for fast evaporation, exactly. In a humid environment, the water in the air is saturated. So for every water molecule evaporating away, there's another one condenses. You break even. You lose heat, and then you get the heat back. No heat loss. But if you put rubbing alcohol or any sort of solvent, that's one that's actually readily available in first aid kits. You put it on the body, there's no ethanol or isopropanol or any other alcohol in the environment. So will it evaporate without worrying about condensation? Will it suck heat out? And the perfect example, how many in lab or when doing fingernails have ever spilled acetone on your skin? And it feels really hot or really cold? It feels really cold. Why? It's at room temperature. The bottle is at room temperature. Not, you don't pull it out of the fridge. You don't pull it out of an ice bath. Why does it feel so cold? Or to quote you, cold magic. It is magic. That is absolutely true. And that's always going to be the right answer to everything. But main reason, it's evaporating. Evaporation equals feels cold. Condensation equals feels hot. And it is pretty amazing that we learn to perspire. But go back to it. Why do our armpits get the sweatiest of all? Going full circle back to something brought up earlier. Friction heat, a little bit. Is it trapped heat? Does your armpit trap heat? Are your arms resting against your body and therefore any heat given off traps heat? So you naturally perspire to try to get rid of that heat. So we get sweaty and disgusting in areas where we trap heat. Just something to keep in mind. I'm going to leave it at that because we're borderline getting into the area where I just think is just vile, but so be it. The heat gained by a colder object always equals the heat lost by the warmer object. Yes, and perfect. The Q, the heat we're talking about is a Q, total heat transfer. So it could be chemical like H, but it could also just be heat existing in the environment. No, then your laptop needs to sweat more. So, in fact, you should tell people when you take the MCAT, if your computer overheats, pour water on it. There you go. Yep. I love you guys. You totally get it. You are so helpful to each other. Just put it in the bathtub. Same with the toaster oven. If your toaster oven is too hot, just throw it right into the bathtub. Oh no, yeah, that's why you get the other person kicked out. You don't get kicked out. MC delta T. One thing that's of interest here, notice the negative sign. Why this negative sign? Where the heck did that come from? MC delta T, and delta T is final minus initial, final minus initial, but notice gained is a positive number, lost is a negative number. Yep, system surroundings, you could also say that. So the environment giving off to the system, or if you will, the system giving off to the environment, you can do it either way. But the negative sign, one is losing, one is gaining. This negative can be erased by moving this back and forth. So I would highly recommend that when you set these things up, you reverse this and make that a positive number. So hot minus final, bigger number minus smaller number, and bigger number final minus lower number, cold initial. But if you always do MC big temp minus small temp, MC big temp minus small temp, you don't have to worry about signs. Okay. And one quick thing, how many have heard of adiabatic, that term? I think there's even a thermos company called adiabat. Adiabatic means no heat transfer. Adiabatic, perfect, well typed. Is that a typo? Or was that spelled correct? So adiabatic means it's perfectly insulated. The best thermos in the world would be adiabatic. Okay, picture-wise, just real quickly, conduction. Heat transfers from a hotter body to a colder body through the following. Results in a thermal gradient. So if I have an initial piece of metal, let's say some rod, 30 degrees all the way, if I were to heat one end and ice down the other, what's going to happen over time? Wow. Can I actually do that? Can it get a hot spot and a cold spot? And can I make a prediction that it should be uniformly cooling down as it goes? Definitely a question they can give you. Heat flows from hot to cold, but does it flow perfectly? Or is it higher temp passes a little bit of energy to lower, which passes a little lower, but heat flows from hot to cold? So perfect. Keep on putting heat in here. It's going to keep on going here, but this is going to keep on taking heat out. So you always end up with a gradient. Thermal gradients, perfect. Did you have time to screenshot that, or did I just totally fat thumbed you? This is true, but I would find it very annoying having to go back and screenshot everything. One thing I'm really curious about is, and this is just hypothetically, let's say one would record it. Would it be good to put in the chat area below it exactly what happens at certain given times? Convection. Convection, heat transfer through a fluid. So why is it better if you're hot to jump into a tank of water rather than to lay against a flat surface that's cold? Yeah, timer energy is a pain. But the one thing I hope happens is, like, there's certain things, like during office hours, I did go over spectroscopy in one, I went over Carnot cycle in one, and went over the PET scan in another. And so those might be good things to have just to go over it. PET scan is friggin' awesome. Okay, what happened in this one? If you saw, hot air rises up, colder air gets pushed down. So generally speaking, where do you want your hot and cold vents if you're trying to heat or cool a room? You want to make the room cooler, your air conditioning duct should be in the ceiling or floor. Actually, the other way around. You want to cool the highest point, because if you put cold on top, hot will hit the cold and it gets cooled down, and cold air will fall to the bottom. Hot air will rise up and you cool it. If you want to heat something up, you heat the floor. So how many ever noticed that in your oven, most of the time when you turn it on, which coil or which flame kicks in near the top or bottom of the oven? Generally speaking, the bottom. Perfect. Because heat will rise, cold air will come down. You heat up the cold air, which will cause it to rise, pushing cold air down. So you get this venting process, this current. So thermal currents, they go like that. Radiation can be done in a vacuum or no? So a couple cool little things about this. Let's consider two surfaces, a black surface and a grayish white surface. Which one is going to heat up faster? Why the black surface? Explain this to me. Perfect. Black surfaces absorb, white surfaces reflect. How many have learned this just over the course of life? How many have done the barefoot walking across the asphalt and sidewalk test over the summer? So when do you let out more profanities? Walking barefoot across the asphalt or barefoot across the cement? Walking on asphalt burns the heck out of your feet because it gets very hot. Okay. Yeah, and that's the thing we forget about with pets, and you walk them on asphalt, unpleasant. Okay, question for you. Does asphalt stay really hot after the sun goes down, or does it cool off pretty fast too? It stays warm after, but does it stay impossible and unpleasant, so hot you can't walk on it? Or does it actually get to a point you could walk on it? So interesting note, black is the best absorber, but it's also the best emitter of heat. So it has no barrier. Light can come in, light can go out. Heat can come in, heat can come out. White surfaces reflect. So what color would you want to make a coffee mug? Ideally. White, because you want it to reflect the heat inside and keep it in. What about if you wanted something to be black? What would that do? I've never heard that phrase, because I always pictured hell as a red spot for whatever reason, but could be. But the back of your fridge is a perfect example. What color is the back of your fridge? Very well played, Jonathan. The back of your fridge is typically black. If you've ever moved a fridge, the black back is black. Wow, it's a tough sentence for me to say. Why do they make the back of a fridge black? It's trying to let heat out. It's built black so that it emits heat. Perfect. So weird question, but the space shuttle, is the space shuttle black or white? It is both. It has a black side and a white side. Why would you need both as a space shuttle? Can you predict whether you're going to need heat or need to get rid of heat? No idea which I'm going to need, but just in case I need heat, I put the black panels towards the sun, like solar panels, they absorb heat. Put the white ones away from the sun. If I overheat, spin it around. Put the white ones near the sun so they reflect incoming light. Black side will give off heat on the other side. So can you actually regulate heat by painting a white side and black side on things? Oh, it's so cool how these things work. Orca wells. I don't know, because they're in a water environment, so I don't know, but I don't know who painted orcas in the first place. But yeah, penguins, I'm generally curious. I mean, you brought up something where I don't know if there is something you said for that, their color scheme for heat. That is, yeah, I want to look this up. Okay, but I'm going to get around that by how cool this is. If light comes in, which one's going to heat up more, the black surface or white surface? Black heats up faster. Let's see if this is true. Here comes these photons. Look at this black surface heating up like crazy. The white surface reflects some of them back. Black surfaces heat faster and cool faster. I know, I freaking love math graphics. Yeah, this is pretty badass, and you had to watch it simply because I took time to make it, dang it. But hopefully it seems okay. You definitely, yep, you're getting your graphics money's worth, dang it. Black finishes hotter, heats faster, cools faster. So generally speaking, we pick colors, black versus white, depending on how we want to thermoregulate. So interesting color, or interesting question, what color are eggs typically? Because they're trying to insulate. And there are definitely some brown eggs as well. So white to brown stays warm, exactly. Okay, interesting that there's something so true about that. So the color of your car will affect its temperature. Yeah, black car in the summer, not the best choice, but you look good. And after all, that's all that matters. Okay, why space shuttle painted the way it is? For that exact reason, so it can give off or absorb heat. How do microwave ovens work? The basic idea. You send in a wave, you heat up the water. So does it shoot random rays or rays specifically associated with water rotation? Targets water. Perfect. Can you heat up dehydrated food very easily? Doesn't work out very well. It burns or it's inefficient. Can be either one. But if you have water content, the bigger the water content, the faster it cooks in a microwave because it's absorbing a lot, but the slower it cooks in real life. Yep, food dries out in a microwave. It is kind of cool. Okay, onward we march. One last type, evaporation, condensation. Just real quickly, evaporation is endothermic, condensation is exothermic. I think we know that. This one is the most rapid way to heat and cool things. So why do people perspire? Peer pressure, like drugs. Gotta admit, that is the best quote of the night. So, Unica, you gave us that one, I think, right? I seriously, I can't wait till the end of lecture so I can tell my wife how smart and insightful the class is, because that's just genius. Seriously, you have totally made my night, by the way. Okay, why is it more susceptible for heat stroke or heat exhaustion in a humid environment? You can't cool off. We can't evaporate without getting a certain amount of condensation. Yep, it's same thing, exactly equal. You are so spot on correct about that. Okay. How can fevers be treated in an environment? So I don't know, like years ago I had a student that why they study this, I don't know, but they studied jungle medicine. And I think partly because they did a lot of international medicine, but that's the one who said that they would sometimes soak a towel in acetone or rubbing alcohol or whatever they had available to them and help like put it on foreheads, whatever. And then I was surprised how many students in the class mentioned that, yeah, that's something I've heard of as well. So Landra, you mentioned something about how Singapore is incredibly humid and hot and miserable at certain times of year. I will bet you anything that's probably a practice that is more common there than it is well, certainly like our little environment here. Yeah, so so Unique, was it actually a common practice in tropical environments? Yeah. And then Jonathan, you've said it so well. I mean, like AC not working is definitely a first world problem. Perfect. Okay. Couple questions, see how you do. Wait, oh, sorry, Brooke, did I just totally screw you over out of a screenshot or just I will click back. Sorry. Actually, you know what? Let me click back real quick. Because, oh, I now know why I click so fast. Because I'm afraid people screenshot it. Yep, this is what we learned in Berkeley Review. So, yeah, this is a great insight I get. People perspire because they like drugs. Okay. So for this one, according to the graph, reaction 1 is. How the heck would I tell if it's insulated or? Oh no, I don't need to delete it. Not at all. No. I'm just no. I'm just totally joking. At this point, the smart aleck comments are perfect. Weird tangent, but when you apply to medical school, is it okay to have any sense of humor? Personal statement. The people who kick ass on the interview, the ones who do really, really well, I know they did answer so fast. The truth is, there's a fine line, but a few schools have been really cool over the years to release the form that they have every interviewer fill out for how they did. And literally one school had a graph like this, a scale from none to well-adjusted to sick and sadistic. They rated candidates on sense of humor. So is it good to have none, good to be sadistic, or good to have just a well-adjusted one? Yeah, yep, you really want your sadistic doctors. You guys totally get it. You get exactly what I'm trying to say. But no, the point being, sense of humor, when it's applicable, is laughter truly a good form of medicine? You bet. So by all means, yeah, well, for a punctured lung, maybe it's not the best thing. Broken rib is not too good. But outside of those, okay. But the point being, humor is a good thing to a point. Don't overdo it, but there's room for it. And they definitely enjoy it more. Smiles beat frowns, laughter beats crying. Because you're gonna have plenty of crying, so laughter is a nice balance. Okay, according to the graphs, reaction 1 is more exothermic. How can I tell if it's more exothermic? What would I look at for exothermic? Final temp, exactly. So the peak is going to tell you, but when you extrapolate over, from a lower peak leads to a lower extrapolated high, higher peak. So how many degree reaction 1 is more exothermic reaction 2? You nailed it. So, okay. How would I tell how insulated it is? The slope, perfect. So if I move those lines down there, would you go reaction 1, it dropped faster than reaction 2. And obviously you can't move lines over like that, but reaction 2 is better insulated because it's not losing heat as fast. Reaction 1 is losing heat more. No, but that's not bad because you got half of it. No, it isn't the delta T. The delta T tells me how much Q equals MCAT, delta T. So it tells me how much heat I got, which tells me how exothermic it is. But in this case, how quickly it loses. So perfectly insulated would look something like this. It would stay flat or barely go down. That's well insulated. That's kind of insulated. That's poorly insulated. That's horrible. Okay. Yes. Everybody see what Brooke just said? I was about to make that suggestion. Your pencil, well, or the writing pen they give you, excuse me, or the scratch pad. And this is something I really want to correct. I apologize that anybody even put that out there from our end, but do you get pencil and paper? You do not. You get laminated graph paper. Most centers, from what I've come to learn now, it's white. Some of the older ones still might be yellow, but it's still laminated graph paper, legal size, 4 pads on a spiral booklet, and you get a pen made by Statler. I think I showed it at one of the office hours or one of the lectures, but it's a fine tip pen, and it's kind of hard to get used to writing with. It's crap, but if you take your fingertips and wet them, recommend your left hand, not your right hand, because that's the one you're going to work on the computer with. Lick your thumb and fingertip, press the tip of that pen. Tell you what, rather than buy one, when we had an in-person class, I bought tons of them. If you want to send me an address, I can send a pen out. If you want to get used to what they're like. I literally do have tons. I think I was showing somebody boxes of the friggin' things I still have. So, but yeah, coordinate by email with me and I'll see what I can do. So it is a garage sale. Let's just say if anybody needs a whiteboard and you're in Southern California, I still have plenty. I have an entire office in my friggin' backyard and garage. Oh, do you really want a whiteboard, Marissa? If you truly do, we're actually within driving distance of one another. I just have all small cars which can't carry a big whiteboard. Let's see. I have one that's 4 by 8 and another one that's thinner that's 6 by 4. So the minivan would probably not hold the bigger one. Okay, for this one, why is line extrapolated? Need to get back in focus, sorry. Correct for heat loss, perfect. Compensates for what you did. Thermometer error is going to be thermometer error. If it's off, it's off. Can't do much about that. Create data points. No, that's just good old-fashioned cheating. You don't need to do anything special to do that. You just do that. Compensate for less than 100? No, you're actually sometimes studying to see if it's less than 100. So, best answer, B as in, boy, everybody picked it, but based on this, wow, I'm actually really impressed. You did better than what the clicker count said back when. Okay, kinetics. Kinetics is going to be just the absolute basics, and I'm going to count on doing a little more kinetics when I do SN1 versus SN2 for reaction order, but for now, I want the absolute fundamentals. The rate of a reaction is defined as how quickly products are formed over time, but would it make sense that the formation of products is similar to the loss of reactants? Because reactants go down as products go up. So could I technically define a reaction either formation of products over time or the rate of loss of reactants over time? How many would agree those both kind of make sense? Okay, that's our basic definition. To monitor reaction then, can I monitor either formation of products or consumption of reactants? And it has to be quantitative. The most common thing we do to measure the rate is based on this equation, which I don't remember, but you're going to help me out what it is. So what is this one? Absorbance equals ECL. How many remember this equation by any chance? Beer's law? The absorbance of light depends on the material and the wavelength you're at, a standard just for what you're looking at, the length of the cuvette, which we keep, but the key thing doesn't depend on concentration. The more stuff in solution, the more light that gets absorbed. So can I see a correlation between absorbance and concentration? Even if I don't know these values, can I safely say if the absorbance doubles, it's because the concentration doubled? So that's how we're going to monitor it. Typically, we monitor using UV vis spectroscopy. That is our most common method. There's other methods, but fairly common. So one of the things that they love to do on the MCAT, Roy G. Biv, 400, 700 or so. So if blah, 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 product is yellow, monitor A, B, C, D. 575 nanometer peak forming, disappearing, 397 nanometer peak forming, disappearing. How many understand my question? I'm just being so lazy about this. And this is real close to something that may very well have been on something I saw once upon a time. So the product is yellow. Is that the absorbed color or reflected color? So what I'm seeing is what it absorbs. Nope, I'm seeing what it reflects. Perfect. So if it reflects yellow, it must have absorbed violet, violet blue, somewhere in that range. So is it a product or reactant? Product. So am I looking for the appearance or disappearance of a peak? The appearance, the formation, and I'm looking for a number around 400-ish. How many get that question? How many understand pick the right peak and decide whether it's appearing or disappearing? Perfect. So we can go the other direction. Let's say, for sake of argument, they said the reactant is red in color. So if it looks red, it's absorbing green. Green is in the 500 or so range. So I would see a disappearing of that, if that makes sense. So appearing or disappearing, product or reactant, and then exactly the wavelength corresponds to the complementary color. You really do need to. Hate to say, but 400 to 700, and let me make this a cleaner look because I'm looking at that, not all that great. The visible spectrum is around 400, so 4, 455, 556, 657-ish, roughly. Yep. Now, the truth is they're not all the same width, so I'm lying to you, but this works for the MCAT, this rough guesstimation. And this is something they specifically put in their handout, their guide to what's on the test. Yeah, numbers are far enough apart that you're not going to come up against that too often. But for anybody who's taking the MCAT, did you use your color wheel on the real thing? Write a little larger? You mean and clear and legible? Can't believe my microprint isn't perfect. Actually, let me put Roy here. Roy G. Biv. This is your 400. This is your 700. Make this around 650, 600, 550, 500, 450, and 400, approximately. Notice I have no indigo. Oh, you're so welcome. And I'm sorry, I didn't mean to be rude. I'm just being a smart ass, and hopefully this works. But Roy G. Biv, so no I, it works out pretty well. And how many learn complementary colors work in the following way? Blue and red make violet, so violet is the complement of the other primary yellow. Red and yellow make orange, so orange is the complement of the other primary blue. Blue and yellow make green, green is the complement of the other primary red. Somebody learned primary, secondary, primary, secondary, primary, secondary. Red and yellow make orange, yellow and blue make green, blue and red make violet. It flows around. So how many are okay with this? This is one of those things that doesn't seem that bad. You can harness it if you know anything about art. But this is critical because of making these decisions. So what appears and disappears. Yeah, hopefully it's popped up with some frequency. Okay, so I'm going to erase this in 3, 2, 1, and now I'm going to throw these other things. So I start out and I take some UV vis, and I find that I have a peak here and a peak here, whatever these nanometers are. And I then run it again, and I notice it was up here, but now this one went down, this one grew in, this one went down, this one grew in. So what disappears? Reactant. So these both are potentially reactants. What grows in? Possibly products. Now I want to be a little more anal because I need to run one more trial. Does this one continue to go down, meaning, yep, looks like a reactant? This one continues to grow, looks like a product. But what did this one do? The last one wasn't there in the beginning, grew in, and then starts to diminish. And this one was there in the beginning, dropped, diminished to almost nothing, then starts to grow back in. So how many would like this better if I said substrate, enzyme, and enzyme substrate complex? By any chance, does that make more sense to you if I write this as substrate, enzyme, and enzyme substrate complex? The beautiful thing is both say the same thing. Your job is to figure out whether biochem or gchem made more sense to you. But either way, substrate is a reactant. It goes down over time. Product is formed. The catalyst is like the enzyme. How many learned that enzyme is there in the beginning, then it becomes part of the enzyme substrate complex, and then its reaction completes, it regenerates the free enzyme. How many have learned that the enzyme gets bound and then regenerates? Meaning it is there in the beginning, it gets consumed, and then regenerated as it grows back in. Enzyme substrate complex is not there in the beginning, it goes in, forms a steady state, hence the Michaelis-Menten steady state approximation, and it diminishes. So over the course of the reaction, I start seeing this relationship. Hopefully it seems okay. So products grow in, reactants diminish. Catalysts are there in the beginning, they get diminished, steady state, and then grows in. Intermediates grow in, this and goes down. So just for sake of argument, that is where Michaelis-Menten kinetics exist. They only exist when the intermediate, the enzyme substrate complex, is in relatively constant or so-called steady state concentration. So excellent question. Going to get that. If you have multiple peaks to choose from, why do you choose the larger one? Because you can monitor it more accurately. You can see small changes in a big number with more precision than small changes in a small number. So you always want to monitor the most measurable thing. So the most intense color is the best one to monitor. Hey, I don't know if you meant a pun, but that is so true. You want to see the one you can see. You see? Okay, and Michaelis-Menten kinetics applies here. Hopefully that seems somewhat familiar to you. Okay, on where we go. Typical graphs. This is one you absolutely have to know. Absolutely positively have to know. The velocity of reaction, also known as the rate. As I add substrate, why does it go up and level off? Somebody please explain to me why it doesn't keep going. Why do you get a maximum velocity? You're absolutely right, but even though dang it, I just totally bumped it, I fat thumbed it. It ends up, is there only so much enzyme to take things on? Exactly, the speed depends on the enzymes. Once you run out of enzyme, you agree excess substrate, it's sitting around waiting for something. So it goes from depending on the substrate, first order, to not depending on it because it's saturated. You can only go as fast as the enzyme can bind it, turn it over, and spit it out. So how many learned something about binding affinity, Km? Oh, they all relate. They all tie together. So binding affinity, Km. I totally forget, but is Km a large one it binds well or a small one binds well? Small number binds well, and here's why. If, how many learned at 1/2 Vmax, Km equals substrate? Is that something you learned that it ends up mathematically that it works out? I'm not going to derive it, it's in the book, but I'm going to tell you that's something we know. So if Km gets smaller and smaller, does that mean you need more or less substrate to reach that? So in other words, if I drew this like this, if I drew another one that looks something like this, would you agree that Km would be larger? I would need more substrate to reach half. This one less substrate. So if it takes less substrate to be half as fast, then it would take less substrate to be completely fast. Less substrate means it must be picking up more efficiently. Smaller Km, better binding. So the yellow one binds better than the blue one. So Km, binding affinity. Okay, Kcat, how well the catalyst can crank things over. So turnover rate from binding to turning it over to spitting it out. So Kcat goes up, helps it go faster. Km goes down, helps it go faster. So how many learned that a really good enzyme is one that has a very good catalytic rate constant divided by Km? So how many learned large Kcat, small Km, and it cranks it out fast? Does that sound familiar? Low Km binds it better. Large Kcat cranks it out. Key terms. Okay, this graph, definitely important. From GChem, it depends on substrate, to now we saturated and it doesn't depend on substrate. It can only go as fast. So in this case, the rate equals some constant, which we're going to call the turnover rate. Oh, catalytic efficiency? Oh, yeah, thank you. So keep in mind, just to be really anal, Km is a capital K on bottom, but Kcat divided by Km. Yep, and it's more efficient the higher the number, exactly. So I need to be careful and really emphasize this. This is a capital K, even though I did a small one. Or think about it, it's a binding affinity, so it should be a capital K type, whereas small k is a rate law. But yeah, so exactly what Tiffany just said. So it's Kcat over Km. The bigger the numerator and smaller the denominator, the better it cranks it out. Okay. Oh, I hit something and nothing happened, so I'm wondering. Okay. Second round of typical graphs. Shoot. In case you didn't get a screenshot, let me toss this out real quick. And Tiffany, thanks for writing that in because I cannot type into the chat box and my writing is atrocious. So I'm going to avoid writing it. Just thank you. Okay, so click if you wish. Now I move on. Oh no. Okay. Typical graphs, these are ones that you have to know more for just seeing data, trends. If the concentration goes down uniformly, then the rate is constant. Because would you agree the tangent at any given point is the same slope? So the rate is constant. Zero order decay then has constant rate. If in the first minute it loses 0.25, the second minute loses 0.25, third minute 0.25 until you run out. First order, a little bit different. First order, the rate now depends. So let me just say the rate is constant. In this case, rate equals some constant. Rate equals now K reactant or K substrate, meaning as the concentration goes down, does the rate get faster or slower? It gets slower and slower because the less you have, less quickly it can go. So the rate diminishes over time. So notice, and this has to do with integrals and derivatives, but this is the derivative here, this derivative here, but notice how these are matching graphs. So this is to the first power, zero power, first power, first power. And so if I start noticing that, hopefully that seems okay. And then finally, second power. So which one drops off faster, second order or first order? I'm so glad. And again, I'm sorry to go really slow, but this is one of those that just really want to do this. So second one, drops off really fast. So here's a question. You are going to give a patient a drug of some sort. Do we have to worry about, just out of curiosity, how much dosing you give? How frequently? Good night. Yes, by all means, your dosing depends very much on this. So if it drops off really fast, do we have to give a bigger or smaller dose? Oh, why does it drop off? Just the natural kinetics of it. That, I hate to say it, but that's a math question. When it's second order, means it depends on the compound squared. So when it drops off, the rate is dropping off not by just the concentration, but concentration squared. So as it drops off, it's exponential drop. Exactly. It drops off really fast because it depends on its squared. But in exchange, I ask you then, which one do you have to give a bigger initial dose? First order or second order or zero order drugs? Biggest dose? Second order, because they decay. But which one lingers in your system apparently much longer? Which one, when they test for it 6 months later as a Major League Baseball player, you get busted for? Second order. Zero order drugs, small dose, but they clear your system, so you got to redose them fairly often. Second order, big dose, but then let it go. Yeah, in that whole relationship, CD over AB, yeah, rate laws. So continual release is not so much the drug, but a design. So are there any materials that slowly dissolve in our system, in our body, in our biological conditions? So I give you a little polymer that breaks down at a consistent rate under biological conditions. Could I infuse that polymer, like make a strand of the polymer, then a drug, strand of the polymer, drug, strand of the polymer, drug? So as the capsule slowly dissolves away in time, does it release another layer and another layer and another layer? So it'd be like having an onion where you put something in between it. Time release is actually pretty tricky. Like healthy and unhealthy carbs, actually, it's a really good example. I don't know. I think so. I think that what it's like, but I don't know if all nerves are suppressed equally like that. But yeah, for a long-term pain block, I think it's initial dose to knock out the nerve, and then a time release to keep it knocked out. So you actually have to do two things, because you can't really you can't like numb you without giving you a big blast at the beginning, and then a time release. So that is my best guess, is that you give the initial dose to knock the nerves out, to reduce the nerves, and then you leave a time release in there. But again, don't quote me on that, because the only MD I have is ordered by mail illegally over the internet. So I don't qualify. But I do believe that's the way it works. Okay. So notice the trend here, half of it from here to here, 50%, 50%, 50%. Is the half-life getting the same, getting smaller, what? Half-life gets smaller, so half-life is useless to me for this one. For the next graph, this one right here, notice half-life, half-life. Is it pretty much the same, even though my drawing isn't so good? Half-life is constant, and then half-life decreases, or increases, excuse me. So decrease, increase. So how many of you ever done this graph where you said 100, half-life goes to 50, to 25, to 12.5. How many have ever done that? Keep on cutting it in half? For first order, if that's 10 minutes, that's 10 minutes, that's 10 minutes. For this one, it'd be 10, 5, and 2.5. Half-life keeps getting smaller. If it's this one, it'd be 10, 20, and 40. So this is the one that it keeps on taking longer time to get rid of half. So is this the one that lingers in your body? Is this the one that clears your body? And this one that sort of are our average. And notice whenever they give you a half-life question, do they always seem to say assume first order decay? Oh, this begets so many possible questions. No doubt about it. Easy questions, mean questions. Drug-related pharmacology questions. You're going to take pharmacology in med school, and this is what you're going to study over and over and over. The process of how drugs clear your body. And it's so utterly cool. And I mean, and again, just knowing the time, the decay rate. And again, it's a weird example, but the asparagus example is such a good one because that tells us the rate of how things clear. I know, isn't that, the concepts aren't bad. You go into so much more detail. Oh my gosh, I wish I remember what the name of the book is, but something Coda is the Bible of kinetics, pharmacokinetics. Kimbo Coda, I think. So help me out on this one. I've walked you into a trick question. You would have to know how much time, but 3 half-lives is a half-life whether it's 0 to first order or second order. Is it still 100 to 50, 50 to 25, 25 to 12.5? So it's still going to be this, 50, that. So if you have 12.5 left, how much did you make? 87.5. So 87.5 out of a possible 100 means your percent yield. How many agree that is a really trick question? Okay, so why is it not A? Because did it ask for how long it took? Or did it just ask for the fact that it just happened? So anywhere did they mention the order or the time, or did they just say that it happened 3 times? Whether it was 10, 10, 10, 10, 10, 5, 2.5, or 10, 20, 30, it still didn't matter. You went 3. It's implied. Oh my gosh, now you're using Carr's words. That's perfect. But I set you up to overthink it. I put you in a frame of mind to overthink it. So I apologize for that. But that's part of the process. So to know that this first one is the one we'll typically do, they can mess with me if they want. Okay, reaction order. Simply put, reaction order tells me how many things the reaction depends on. What does the letter, our letters RDS stand for? Rate determining step, meaning can you go as fast as the slowest step? Life is an assembly line. If your job is to pick up a package and put it on a desk, next person's job is to pick it up and run it from that desk to another desk, and then this person over here picks it off that desk and stacks it. Which is going to be faster, picking it up, running across the room, or putting it down? How many agree fast, slow, fast? Picking it up and putting it on the table, relatively fast. Picking it up, running it all the way across, slow. Taking it off the table and stacking it, relatively fast, which means it can only go as fast as the middle step of the assembly line. The rate determining step is your slowest step. So the rate depends on that which involves the slowest possible step. How many have done this example many, many times where you look at what happens when I double A, B stays constant, what happens to the rate? Two times. So A to what power equals, or 2 to what power equals 2? Depends on A to the first. Perfect. B, so no change, doubled and no change. So B to the 0. B to the 0 is 1. That's how much it changed. So this depends on A only. So the rate here equals K times A. This one, it can either depend on something squared, or in this case, can it be the same thing we just did? 2x, so A to the first, and then B, 2x, so B to the first. So for this one, can we say rate equals K AB? So I would say it is first order with respect to A, first order with respect to B, but overall second order because the rate depends on two things. Just a point of interest, this is the SN2. The 2 stands for second order. SN1 stands for first order. And this is Vmax where it's saturated. Those are the examples you have to know. Vmax is 0 order, constant rate. SN1 depends on only one thing, the electrophile. SN2 depends on the nucleophile and the electrophile. How many have done these tables before, didn't like them then, not liking them now too much? I'm so appreciative. 3 hours in, your mind can still be blown. It's just awesome. So it ends up, it's like it ties together. It's just in GChem, they just randomly presented it. But now that you have context from other classes, hopefully it makes it all fit in. And that's really what it comes down to, is just the fact that, damn, this all fits into things I've learned, but they mention different aspects of the same thing. You're looking at the puzzle when all the pieces are come together. Okay. Well, I hopefully will become one starting in January. I'll let you know. But a few questions. Oh, did I screw you guys out of the screen again? Okay, so screenshot if you wish. Oh, K, come on. K is clearly the first letter in the word constant. So yeah, again, spelling is not our strength in science. So K is a rate constant. So what are the things that would affect the K? Because it really isn't much of a constant. And that's going to be one of the questions that pops up soon. It's a given for reaction under the following conditions. How many learned that if you change the solvent, you can actually change the type of reaction from, let's say, I don't know, polar to nonpolar, protic to aprotic? The solvent type affects K. The Arrhenius equation exactly affects it. So are there some reactions where they just collide very specifically as be like an SN2 backside attack? Not every reaction, not every collision equals a reaction. And temperature, does temperature change a rate somehow? So K, we're going to run into an answer to one of the questions, so I'm going to ignore the rest of it for a second. Yeah, you have to have an aprotic for an SN2 and a protic for an SN1. Technically, you don't have to, but it facilitates it. So in an SN1, you want it to tear apart. So a protic solvent binds the leaving group, pulls it off, binds the intermediate and stabilizes it, stabilizes those ions you get in SN1. Aprotic, because it doesn't stabilize ions, doesn't encourage ion formation, which means it doesn't encourage breaking apart. It favors the SN2. And again, that I'll deal with that down the road, but probably if you want to add one more thing to this, protic and aprotic favorability. So it doesn't have to be, but it prefers protic. Doesn't have to be, but it prefers aprotic. Okay. I'll give you a few seconds on this one. so sorry to give you more time than intended, but for this one, so when we monitor this, what happens to a solvent peak? Stays constant, pointless. Catalyst, what will happen to a catalyst peak? Catalyst will decrease and then go back, exactly. If it's a reactant, it'll decrease, perfect, not increase. Hard or easy question? Certainly, I gave you way too much time, I apologize. Partly went over it, but I think that's also one of those things that you would deduce. This is the Arrhenius thing, the Arrhenius equation. So Tiffany, I apologize because I totally blew off your sentence or your statement earlier because I was trying to save it for this. But you're absolutely right. Depends on A. Yeah, the parallel to enzyme substrate makes it so much easier. It really does. But how many learn the constant depends on a few things? Depends on the activation energy, depends on the temperature, and it depends on the Arrhenius constant. So let's just say if I increase the temperature, what's going to happen? So if the temperature goes up, what happens to this overall value? Bigger denominator makes that fraction smaller because it's a negative. A smaller negative actually means this is bigger. So that whole quantity is larger. So increasing temperature makes K go up. How many didn't need to do the math? How many just know you heat something, give it more energy to overcome the activation barrier so it reacts faster? So kinetic theory of gases approach is better than math. Okay, adding catalyst. What does a catalyst do? Ooh, let me color coordinate this the right way. K goes up. If I add a catalyst, activation energy goes down. Same story. If this is small numerator, smaller number, but less negative means bigger, K goes up. How many have learned adding catalyst makes it go faster? Yeah, relationships matter. Equations matter for which things happen or cause and effect in relationships, not calculations. Okay, well, adding more reactant in the rate determining step, sure, because that's rate equals K times your reactant in the rate determining step. So if that goes up, rate goes up. Finally, what does solvent do? Does solvent have any bearing on anything? Solvent has a different impact. Solvent dilutes this. If you dilute the concentration of a reactant, reactants go faster or slower. They end up going slower. So this one lowers concentrations, including the rate determining step ones. So in OChem, did they ever tell you to quench a reaction by dousing it with solvent? I think knowing the rate equation is still good. I think that's a good idea. Okay, perfect. So for this one, I'm going to erase what I've written. It's going in 3, 2, 1. No, okay. So so here's what popped up in chat box. I'm confused how D lowers, but you said SN2 needs more protic solvent. So it needs not a more protic solvent, it needs a protic solvent instead of aprotic. So I'm not saying that adding more protic solvent makes it go SN1. I'm saying a protic solvent, whatever quantity of protic solvent we have, helps it to go by an SN1 mechanism. But if I add more and more solvent, then I dilute it so much that it collides more often or less often. And so in that sentence, more protic doesn't mean more as in quantity of protic, but one that is a higher degree of protic nature to it, if that makes sense. Okay, erasing everything in 3, 2, 1, gone. And now for the better equation. So here's this. And rate constant, K, equals Arrhenius constant, E this to this. So as mentioned, temperature goes up, K goes up, we deduce that. The catalyst lowers activation energy, did that. Adding more solvent does that. And then finally, diluting everything, or not adding more solvent, excuse me, adding more reactant. It's going to increase the rate, but then hopefully that makes sense. Okay, this one I want to give you about 30 seconds. For this one, same thing as before. 2 times. 2 times. So would you agree it depends on A to the first, which gets rid of that and that. Okay, so we're good on that one. B goes up 2 times. This is where it's tricky. Did the rate go up or down? So anybody see how it actually went up? Went up because that damn power of 10. So this is really 12 times 10 minus 3. So it went up 2. So it also depends on B to the first. So because of that, best answer, it depends on both A and B. How many got because the rate changed with A and rate changed with B, it had to be something that had both? So even if I didn't know the math exactly, I know that changing A changed the rate, changing B changed the rate. So it had to depend on both. And then finally, last but not least. Yeah, see, that's awesome. So even if you don't do it perfectly, if you still have a logical, good way to get it, that one changed and the other changed and they both changed, that's solid. That's a kind of logic. This one, you have about 20 seconds to get right. So how does 520 compare to 130 or 130 compare to 520? Half of a half, 1/4 exactly. So 130 divided by 520 equals 1/4, which means how many half-lives? 2 half-lives, perfect. So it's 2 half-lives total, which means second half-life, 260, 130. First half-life was 520 to 260. What is the total time of the whole process? 32. So what is each individual segment? 16. Perfect. So how many are okay with that? How many have definitely experienced this exponential growth or half-life, half whatever? Once upon a time, and I don't want to say where, but let's say I was standing in a or sitting in a room with a bunch of other people taking a standardized test. They might have talked about if you start 4 feet from a wall and you undergo 3 half steps or 3 half movements, how close are you? So from 4 to 2, 2 to 1, and 1 to half, you were 6 inches away. How many agree? What a bizarre question. But occasionally they do weird stuff. Yeah, I don't even know what I said either, but let's say you're 4 feet away from a wall, and 3 different times you cut your distance in half. You go half distance. So from 4 to 2, you cut your distance in half. And from 2 to 1, you cut your distance in half. And from 1 to a half. So you're half feet away from the wall after 3 half distances. How many agree that's just somebody going out of their way to be weird? But it works. Why? Because you'll be a better doctor. Because now, understanding that, you'll be able to diagnose so much better than before. Oh, of course. I have no idea. No idea. But, I mean, occasionally there's some bizarre questions. I think that's this case of a test writer trying to test you on this concept of half, half, half in a different situation. So half-life is simply the amount of time it takes for whatever quantity you have to be cut to half its value. Half of 520 is 260. So the time it takes to get 260 first half-life, 260 to 130, cutting in half, the second half-life. Because it is first order decay, 16 and 16. So hopefully that seems okay. Leading to one last thing you absolutely have to be able to do, and that is recognize secret messages. So what does it say? Time to chill out or spend some of your enthalpy on homework? Okay, it's not a really hard one to solve. But again, I do apologize, longest one yet, and that's because it's 2 lectures stuck into one. And again, I don't know how the heck that got scheduled that way. Thermo and kinetics are generally different. And again, same thing. I apologize for the length, but I think if you go too fast, you don't get it. But hopefully this puts things into place. And now we're ready to take on biochem approach to this. Oh, thank you guys so much. I appreciate it. I've overstayed my welcome too. So I actually, din time. I was supposed to actually take care of that a while back. So actually, let me check, just scrolling through. Oh yeah, so just the whole black and white surface thing, for whatever reason, black surfaces absorb better and they're non-reflective, they're absorbing. So what color do you make a solar panel? Night, night, Phyllis. Black, why? You want a solar panel to absorb light. What color do you make a surface of anything you want to absorb energy? Make it black. But we also paint surfaces black to emit heat as well. Possibly, black hole is absorbing all matter. So black hole is more along the line of gravitational, but yeah, it sucks things in past a certain point. Yep, black surfaces absorb and emit energy, heat, light, better than any other color. So, okay, so good question. Why does it emit better? Well, if absorption means light can easily go into it, there's nothing preventing light from going in, would it make sense there's also no gatekeeper, nothing interfering with it leaving as well? So black can take on and give off waves much easier than a white surface. White surface doesn't absorb as much. It reflects. Shiny surfaces, because they have less surface area. When you smooth something out, make it flat, less contact area, less absorbing as well. So if you want to make something very absorbent, you make it black and a rough corrugated or serrated sort of surface. Whereas if you want to make something reflective, you make it white and smooth on top. So hopefully those things seem okay. Anyway, I will call it a lecture. So thank you guys for sticking through everything. And again, sorry, this will be the longest one by far. That's because we combined what should have been 2 lectures. Oh, you're very welcome. So I'm going to go ahead and exit out of this. Oh, actually, yeah, that was the other slide that kicked in. So with the sprinkles.